Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring some of the most profound and perhaps unsettling contemplations, the scariest solutions to the Fermi Paradox, specifically the Great Filter and dark forest theory. Before we gently immerse ourselves in these cosmic enigmas, I would like to know where you are at this moment. Perhaps you are curled up on a window seat, listening to the gentle rhythm of rain against the glass. Or maybe you are wrapped in a soft blanket, watching distant city lights fade into the quiet expanse of the night. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe, allow your eyes to grow heavy, and let's begin. The universe, in its immense and silent grandeur, presents us with a profound cosmic riddle, one that has captivated thinkers and scientists for generations. It is known as the Fermi Paradox. At its heart lies a striking contradiction. Given the sheer scale of the cosmos, the countless stars, and the abundant planets, the probability of advanced civilizations existing elsewhere seems extraordinarily high. Yet, when we gaze into the night sky, when we listen with our most sensitive instruments, we are met with an echoing silence. Where is everyone? This question, simple in its phrasing, opens a chasm of possibilities, some of which are deeply thought-provoking, perhaps even disquieting, inviting us to ponder the very nature of life and its journey through the vastness of time. Consider for a moment the sheer statistical likelihood of life beyond our Earth. Modern astronomical observations, particularly those from missions like the Kepler Space Telescope, have revolutionized our understanding of exoplanets. We have discovered that planetary systems are not merely common, but ubiquitous. Most stars, we now understand, host planets, often several. Our own Milky Way galaxy alone contains an estimated 100 billion to 400 billion stars, each a potential sun for orbiting worlds. And a significant fraction of these planets, perhaps 1 in 5, are believed to reside within the so-called habitable zones, those orbital sweet spots around their host star where temperatures are just right for liquid water to exist on a planet's surface. Liquid water, as we know, is a fundamental prerequisite for life as we currently understand it, serving as a solvent and a medium for biochemical reactions. This means there could be tens of billions of potentially Earth-like planets within our galaxy alone, each a potential cradle for genesis. If we then extrapolate this incredible abundance to the observable universe, which contains hundreds of billions of galaxies, each a colossal island of stars, the numbers become truly staggering, almost beyond our intuitive grasp. The potential for life, for its emergence from primordial chemistry, for its evolution through countless eons, appears almost boundless. Furthermore, the very building blocks of life, complex organic molecules like amino acids and nucleobases, are found throughout interstellar space, observed in nebulae, comets, and protoplanetary disks. This cosmic ubiquity suggests that the raw materials for biology are not exotic rarities, but are readily available across the cosmos, patiently waiting for the right conditions to assemble into something more complex. The famous Drake equation, though not yielding a precise numerical answer, serves as a conceptual framework, a sophisticated thought experiment, guiding us through the various factors that would determine the number of detectable civilizations. It suggests that if even a tiny fraction of these potentially habitable worlds were to give rise to life, and if a minuscule percentage of that life were to evolve into intelligent technological civilizations capable of interstellar communication, then the universe should, logically, be teeming with them. The very fabric of space-time seems to whisper of life's potential, woven into the cosmic dust and gas that forms every new star and planet, echoing a common cosmic narrative that should, by all accounts, include countless voices. We might then expect to see tangible evidence of these advanced civilizations. Perhaps grand engineering projects, often termed megastructures by futurists like Freeman Dyson, such as colossal spheres built to entirely encompass stars and capture their vast energy output. Such structures would dramatically alter a star's light signature, dimming it or shifting its spectrum in ways that our most powerful telescopes, like the James Webb Space Telescope, could perceive across immense distances. Yet, despite diligent searches, no definitive Dyson spheres or other obvious signs of astroengineering have been discovered. Or perhaps we would intercept clear, unambiguous radio signals, deliberate messages intended for detection, or even the incidental radio leakage, the electronic chatter of a technologically advanced society going about its daily cosmic business. For decades, dedicated projects like SETI, the search for extraterrestrial intelligence, have meticulously scanned the heavens, listening intently across a wide spectrum of frequencies for any sign, any whisper, any mathematical pattern that might betray the presence of another intelligence across the vast interstellar distances. Yet, the cosmic airwaves remain largely quiet, a profound testament to an absence that defies our statistical expectations and prompts a deeper inquiry into the profound silence that surrounds us. This absence is not merely a lack of discovery, it is a fundamental challenge to our assumptions about life's prevalence and destiny. This profound discrepancy between the high statistical probability of widespread intelligent life and the stark, persistent lack of observational evidence is what Enrico Fermi, the Nobel laureate physicist, famously pondered during a lunchtime conversation in 1950. "Where are they?" he asked, a question that has since become synonymous with this cosmic enigma. This query continues to resonate, not just as a compelling scientific puzzle that challenges our understanding of biological and technological evolution, but as a deeply existential one. It forces us to confront our unique place in the universe, to question whether our existence is a common occurrence, a fragile anomaly, or perhaps something even more singular, a fleeting moment of self-awareness in an otherwise barren expanse. What does this silence imply for us, for our future? The answers, or rather, the proposed solutions to this paradox, range from the scientifically plausible to the truly terrifying, each inviting us to look inward as much as outward, to consider not merely the potential for advanced life, but the myriad perils and thresholds that might prevent its flourishing across the boundless cosmos. They suggest that the silence we perceive might not be an accidental quirk of the universe, but rather a deliberate quiet, or perhaps a consequence of universal laws and evolutionary great filters that we are only beginning to comprehend. The possibilities lead us to consider not just the potential for advanced life, but the profound vulnerabilities inherent in its development, the critical junctures that might prevent it from reaching interstellar scales, or perhaps the compelling reasons why any truly intelligent life, if it exists, might choose to remain profoundly hidden. These are the contemplations that invite us to reflect on our own journey, our own fragility within the cosmic tapestry, and the enduring, sometimes unsettling mystery of existence itself. We are left to wonder whether our cosmic solitude is a blessing or a warning, a unique moment in time or a prelude to a universal truth, yet to be unveiled. The implications of this silence are vast, shaping our understanding of everything from astrobiology to the potential future of humanity, urging us to consider the profound implications of an empty sky. It is within this profound quiet that we begin to seek answers, turning our attention to the more somber explanations that attempt to resolve Fermi's unsettling question, and in doing so, perhaps illuminate our own destiny. The profound silence of the cosmos, which we just contemplated, leads us naturally to consider one of the most compelling and, for some, deeply unsettling explanations for the Fermi Paradox, the concept of the Great Filter. This idea, first articulated by economist Robin Hanson, posits that somewhere along the vast evolutionary path from the very first stirrings of life to a technologically advanced interstellar civilization, there exists a formidable barrier, a critical step that is exceptionally difficult, perhaps even impossible, to overcome. This filter, a kind of cosmic bottleneck, would explain why, despite the statistical likelihood of life emerging and evolving, we observe no other advanced species capable of interstellar travel or communication. It suggests that something universally prevents life from reaching a stage where it could colonize galaxies or send out detectable signals across the void, leaving us in our profound cosmic isolation. The Great Filter is not necessarily a singular catastrophic event, but rather a sequence of challenging hurdles, each representing a profound test to life's persistent march toward complexity and cosmic reach. The precise location of this Great Filter is what truly shapes our understanding of our own place and prospects within the universe. Is it a formidable challenge humanity has already overcome, a difficult evolutionary threshold firmly in our past, or is it a terrifying ordeal that still lies ahead, a looming existential threat that awaits all nascent intelligent species? The implications of each possibility are vastly different, painting either an optimistic or a somber picture of our cosmic solitude, compelling us to reflect deeply on our own trajectory through the cosmic narrative. If the Great Filter lies firmly in our past, then humanity, by its very existence, has already navigated one or more incredibly rare and difficult evolutionary transitions. This scenario suggests that the emergence of life itself, or its subsequent development into complex multicellular organisms, or perhaps the leap to self-aware intelligence and sophisticated tool-making, are far more improbable than our current models might suggest. Let us consider the very first step, abiogenesis, the intricate process by which non-living matter gives rise to self-replicating, evolving biological systems. While scientists have made remarkable progress in laboratories, synthesizing complex organic molecules under conditions believed to have existed on early Earth, the spontaneous assembly of these components into a fully functional, self-sustaining life form remains a profound mystery, a leap across an immense chasm of complexity that may defy simple statistical expectation. It might be an event so exquisitely rare, so sensitive to a precise confluence of environmental conditions that it has occurred only once, or perhaps a mere handful of times, across the entirety of our observable universe, making our vibrant planet, Earth, truly exceptional. Alternatively, the filter could be a later, yet still ancient, evolutionary bottleneck, one that occurred long before the advent of complex societies. Perhaps the transition from simple prokaryotic cells, which lack a nucleus and other specialized organelles, to complex eukaryotic cells, a process that took billions of years on Earth, represents an enormous increase in biological organization and energy efficiency that few nascent life forms ever achieve. The subsequent development of sexual reproduction, which dramatically increases genetic diversity and evolutionary adaptability, or the Cambrian explosion of diverse multicellular life forms, which saw the rapid appearance of most major animal phyla and body plans, could also be considered potent filters. These events represent profound shifts in biological architecture, ecological interaction, and the very blueprint of life's potential. If any of these early steps in life's long journey are indeed the Great Filter, then the silence we perceive is not a warning of impending doom, but rather a testament to our extraordinary and singular journey, affirming our rare and precious existence. This perspective, while perhaps instilling a sense of cosmic loneliness, also offers a profound sense of safety, suggesting that the most difficult challenges are behind us, and our path forward, though uncertain, is not predetermined by an inevitable cosmic catastrophe awaiting all intelligent civilizations. We might be among the very first, or perhaps the only, intelligent life to have reached this stage. A solitary beacon in a quiet cosmos, tasked with carrying the flame of consciousness forward through the boundless reaches of time. However, a far more chilling possibility, one that demands our sober contemplation, is that the Great Filter lies in our future. This would imply that the emergence of intelligent life capable of interstellar communication is a relatively common occurrence across the universe, but something universally prevents such civilizations from enduring or expanding beyond their home systems for extended periods. In this unsettling scenario, the cosmic silence we hear is not an empty void, but rather a vast, silent graveyard, a chilling testament to the common, tragic fate of all advanced civilizations that fail to navigate this ultimate test. What could such a future filter entail? One prominent and often discussed idea is self-annihilation. As civilizations become more technologically powerful, the very tools and capabilities they develop to master their environment also grant them the means to inadvertently or deliberately destroy themselves. This could manifest in various equally devastating forms. Global nuclear warfare, fueled by escalating geopolitical tensions and the proliferation of destructive weaponry. Uncontrolled artificial intelligence, evolving beyond human control and purpose, perhaps viewing its creators as an obstacle. Genetically engineered pandemics, released accidentally or intentionally with unforeseen and catastrophic consequences. Or irreversible environmental collapse. A consequence of unchecked technological growth, unsustainable resource exploitation, and a failure to adapt to planetary limits, pushing our ecosystems beyond recovery. Our own historical trajectory, marked by both incredible scientific and technological progress alongside periods of devastating conflict, ecological degradation, and the constant struggle for global cooperation, provides a sobering illustration of this potential vulnerability. The very ingenuity that allows for advanced technology also creates unprecedented, often unforeseen, existential risks that might prove insurmountable. Another possibility is a natural, unavoidable cosmic catastrophe, such as a sudden, intensely powerful gamma ray burst from a distant collapsing star, a nearby supernova event, or a planet-killing asteroid impact, against which even highly advanced technology might offer insufficient defense, especially if the civilization has not yet achieved widespread interstellar dispersal and thus remains vulnerable on a single world. Perhaps interstellar travel itself, though theoretically possible, is inherently dangerous, prohibitively expensive, or simply too slow and resource-intensive to allow for widespread colonization, leading to isolation and eventual decline of individual civilizations before they can establish a robust, multi-world presence. Or perhaps, and this is a particularly unsettling thought, advanced civilizations invariably reach a point of technological stagnation or existential ennui, losing the collective drive to explore, expand, or communicate. Retreating inward until they fade into obscurity or transform into forms unrecognizable to us, becoming undetectable by our current methods. A quiet fading rather than a violent end. This future filter hypothesis suggests that the apparent absence of extraterrestrial intelligence is a dire warning for humanity, a cosmic mirror reflecting the precariousness of our own future. It implies that we are not special for having come this far, but rather that we are approaching a universal test, a monumental challenge that very few, if any, civilizations ever pass. The silence, then, is not benign. It is a profound cautionary tale, urging us to navigate our technological and social development with the utmost care and foresight, aware that the very path we are on might lead to a common, silent end. This quiet reflection, while perhaps touching on concepts of deep cosmic peril, is meant to evoke contemplation, not fear, reminding us of the immense stakes in our journey through the universe. The Great Filter offers a powerful framework for understanding the silence of the cosmos, positing a universal barrier to advanced life. Yet, there is another, perhaps even more chilling, hypothesis that attempts to resolve the Fermi Paradox, one that shifts the focus from intrinsic developmental hurdles to the very dynamics of interspecies interaction across the vastness of space. This is known as the dark forest theory, a concept popularized by the science fiction author Liu Cixin in his novel of the same name. It paints a stark yet logically consistent picture of a universe where advanced civilizations, if they exist, choose to remain profoundly silent, not because they cannot overcome a filter, but because they fear what might happen if they reveal themselves. Imagine the cosmos not as an open, welcoming expanse, but as a dense, silent forest stretching into infinity, filled with countless hidden hunters. Each hunter represents an intelligent civilization, and each is acutely aware of its own vulnerability in this vast, unknown wilderness. In such an environment, the most rational strategy for survival is silence. To reveal oneself is to invite potential destruction. This theory suggests that any civilization capable of interstellar travel or communication would quickly realize the inherent dangers of broadcasting its presence. For in a universe of unknown intentions, an unknown entity is always a potential threat. It is a cosmic game theory played on the grandest stage, where the optimal move for every player is to conceal their existence and, if necessary, eliminate any perceived threat. The core tenets of the Dark Forest theory stem from a few fundamental assumptions about the nature of life and civilization on a cosmic scale. Firstly, the drive to survive and expand is considered universal. Any civilization that reaches a high level of technological advancement would likely possess the means and the motivation to seek out new resources, new planets, and new systems to ensure its long-term viability. This inherent expansionism, when applied to a galaxy with finite resources, inevitably leads to competition. Picture the vast, shimmering spiral of a galaxy, a cosmic garden filled with worlds, some barren, some brimming with potential. Each civilization, like a growing plant, requires sustenance and space. If two such entities encounter each other, they are immediately in potential competition for these vital, finite resources. Secondly, it assumes that communication across vast interstellar distances is inherently difficult and agonizingly slow. Light speed limits mean that messages could take hundreds or thousands of years to reach their destination, and any response would take just as long. This immense time lag makes meaningful dialogue, nuanced understanding, alliance formation, or even a clear assessment of another civilization's motives virtually impossible. If the time it takes to exchange a single message spans entire epochs of a civilization's history, how can trust or shared purpose be genuinely established? Without the ability to truly understand another, to discern their intentions and capabilities in real time, the safest assumption becomes one of potential threat. The profound temporal gulf between any two communicating species renders diplomacy nearly impossible and immediate assessment crucial, often leading to the most conservative and thus most aggressive conclusions. This leads to the third and perhaps most critical assumption, the chain of suspicion or the technological explosion. If you detect another civilization, you cannot know its intentions. It might be peaceful, seeking only companionship or shared knowledge, or it might be hostile, driven by expansion or fear. But if it is hostile, and if it is more technologically advanced than you, then your existence is immediately imperiled. The danger is amplified by the potential for rapid technological growth, a technological explosion. A civilization that is only slightly more advanced than you today could become overwhelmingly superior in a relatively short cosmic timescale, perhaps within a few centuries, rendering any defensive measures utterly futile. Therefore, the safest course of action in this grim cosmic calculus is to eliminate any potential threat before it can develop into an existential danger. It is a preemptive strike, not necessarily born of inherent malice or a desire for conquest, but of a cold, rational logic of self-preservation in an uncertain universe where the stakes are absolute. Consider the act of sending a signal into the cosmos, an attempt at active SETI, or messaging extraterrestrial intelligence. From the perspective of the Dark Forest theory, this is not a gesture of hopeful outreach, a beacon of friendship across the void, but an act of profound recklessness. It is akin to shouting loudly in a dark forest, revealing your precise position to all who might be listening, without any knowledge of their nature, their intent, or their capabilities. Such a broadcast would immediately mark you as a potential target, a resource to be acquired, or a competitor to be neutralized. The energy cost of destroying another civilization, especially one far away, might be far less than the cost of managing it, negotiating with it, or competing against it for resources over galactic scales. Thus, the most efficient and safest action for an established, advanced civilization might be to destroy any nascent intelligent life it detects swiftly and silently before it becomes a formidable, unknowable threat. This act would be less about aggression and more about cosmic hygiene, a means of clearing potential competition from the galactic stage. This chilling logic suggests that the absence of extraterrestrial communication is not merely a lack of life, but proof of a universal cosmic strategy. Those who survive are those who remain hidden. Those who make noise, those who seek to explore or communicate too openly, are swiftly extinguished, their signals fading into the cosmic background as a silent warning to any who might follow. The implications for humanity are profound. Our nascent attempts at broadcasting our presence, our eager search for a response, might be seen as naive, even dangerously optimistic. It prompts a reevaluation of our role in the cosmos, shifting from hopeful, curious explorers to cautious inhabitants of a potentially hostile environment. The night sky, once a boundless canvas for dreams and wonder, transforms into a silent, watchful realm where the absence of light is not emptiness, but perhaps a profound, deliberate quietude, a veil behind which countless entities may be hiding, waiting, or observing. It is a universe where the most advanced life forms are the quietest, the most adept at concealment, having learned the ultimate, sobering lesson of survival. In the dark forest, silence is not merely golden, it is essential for continued existence. This perspective, it suggests that the beauty and silence of the night sky may conceal a hidden, complex interplay of survival strategies. Find ourselves asking, if this theory holds true, what does it mean for our future? Should we continue to listen, to send messages, or should we embrace the quiet, hoping to pass unnoticed in the vast, silent expanse? The very act of asking these questions reshapes our perception of the universe, transforming it from a benign stage to a complex, strategic arena, where wisdom lies not just in knowledge, but in understanding the profound implications of our presence and our actions. This silent, contemplative thought about the universe's ultimate nature, even one so stark, can lead to a deeper appreciation of the quiet, delicate balance of our own existence. The profound implications of the Great Filter and Dark Forest theories lead us to a pivotal crossroads in our contemplation of cosmic existence. If the universe truly operates under such conditions, then our approach to the search for extraterrestrial intelligence, and indeed our very understanding of our place within the vast cosmic tapestry, must be profoundly reevaluated. The innocent wonder of simply listening, or worse, actively broadcasting our presence into the silent void, transforms into an act fraught with potentially monumental consequences. Consider the ongoing efforts of unwind, which diligently scan the heavens for any whisper of another civilization. If the Great Filter lies in our past, then our current solitude is a testament to our remarkable, perhaps unique, survival. In this optimistic view, our continued listening is a hopeful endeavor, a patient vigil for others who may have also navigated the improbable path to intelligence. However, if the filter awaits us in the future, then our search becomes a desperate attempt to find fellow travelers on a path destined for a common, perhaps unavoidable, demise. The silence, in this context, is a premonition, a cosmic silence before a storm that has claimed all others. Now, let us turn to the more active side of this endeavor, METI, or Messaging Extraterrestrial Intelligence. This involves deliberately sending powerful signals into space, announcing our existence and location to any potential listeners. From a purely hopeful perspective, METI is a courageous act of cosmic outreach, an invitation to dialogue, a testament to humanity's yearning for connection. But through the lens of the dark forest theory, such an action is transformed. It becomes an act of profound, almost suicidal, naivety. To broadcast our presence is to potentially reveal ourselves to an unknown predator, a more ancient and powerful civilization that, driven by a cold logic of self-preservation or resource acquisition, might view our emergence not as a cause for celebration, but as an existential threat to be neutralized swiftly and silently. The vast distances and time lags of interstellar space mean we cannot know the nature of whom we might awaken. A message sent today might reach a listener in 1,000 years, and their response, if one were even sent, would take another 1,000 years to return. In this immense temporal gap, a civilization's intentions, its technological capabilities, and its very motivations could change dramatically, rendering any initial assessment utterly meaningless. The risk, from this perspective, is not merely a lack of response, but the initiation of an irreversible sequence of events that could lead to our undoing. This contemplation forces us to confront a profound ethical dilemma. Is it our right, or indeed our responsibility, to announce humanity's presence to the universe, potentially jeopardizing not just our species, but all life on Earth? Or is it our greater duty to remain hidden, to quietly observe, to strive for a deeper understanding of the cosmic landscape before making such an irreversible decision? Some scientists, like Stephen Hawking, famously warned against active METI, suggesting that any advanced civilization encountering us might not be benevolent, but rather akin to European explorers encountering indigenous populations, a scenario that historically rarely ended well for the less technologically advanced party. This perspective does not necessarily assume inherent malice, but rather the universal drive for resources and the potential for technological disparities to lead to domination, or worse, eradication, even if unintended. Furthermore, the silence itself could be a form of communication, a universal warning. Perhaps the most intelligent civilizations have already learned the hard lesson that openness leads to vulnerability. They might have passed through their own great filters, survived their own existential crises, and emerged with a profound understanding of the cosmic game. To be seen is to be at risk. Their advanced technology might allow them to mask their presence perfectly, to exist in a state of undetectable equilibrium, or even to manipulate space-time in ways we cannot yet conceive, making their signals indistinguishable from natural cosmic background noise. This silent watcher's hypothesis suggests that the most successful civilizations are those that have mastered the art of non-interference and perfect camouflage, becoming cosmic ghosts, observing without being observed. Their very absence from our detectable universe would then be the most significant piece of information they could provide, a chilling lesson in self-preservation. This leads us to a fascinating, if somewhat humbling, thought. Perhaps our current understanding of what constitutes a detectable civilization is fundamentally limited. We search for radio waves, for Dyson spheres, for patterns we can comprehend. But what if truly advanced life has evolved beyond biological forms, into pure energy or information, existing in computational substrates that transcend our physical universe? What if they have retreated into black holes, or constructed intricate pocket universes, or simply achieved a level of consciousness that no longer requires a physical presence, becoming a part of the cosmic fabric itself in ways we cannot yet fathom? These possibilities suggest that the silence is not necessarily an absence of life, but an absence of life we can recognize or detect. The filter in this sense is not destruction, but transformation beyond our current observational capabilities, leaving us in a universe that appears empty only because our senses are too crude, our paradigms too narrow. The weight of these ideas, the great filter and the dark forest, rests heavily upon our collective consciousness. They are not merely abstract scientific puzzles. They are profound reflections on our own fragility, our potential, and our responsibility. As we drift through the silent depths of space and time, gazing at the distant stars, we are reminded that our understanding of the universe is still in its infancy. The question of where is everyone might not have a comforting answer. It might instead demand of us a deeper wisdom, a more cautious approach, and a profound appreciation for the fragile miracle of our own existence. To navigate this cosmic labyrinth, we must not only seek knowledge, but also cultivate humility and foresight, understanding that our loudest declarations might be our most dangerous, and that true cosmic wisdom might lie in the art of quiet observation, allowing the universe to unveil its secrets at its own pace and on its own terms. This awareness, while contemplating the vast unknown, can paradoxically bring a sense of calm, a realization of the delicate balance we inhabit within the grand, silent expanse of the universe, urging us to cherish our moment of conscious awareness and to proceed with thoughtful deliberation, ever mindful of the profound implications of our cosmic solitude and the choices we make within it. We are, after all, a part of this unfolding mystery, and our journey is but a brief, luminous flicker against an ancient, silent backdrop, a testament to the enduring wonder of being. The previous contemplation on the Great Filter and the chilling implications of the dark forest theory naturally leads us to ponder our strategic response. Should these hypotheses hold even a kernel of truth? If the cosmos is indeed a dangerous realm where revealing one's presence is an invitation to peril, must shift from optimistic outreach to prudent, perhaps even fearful, caution. The very act of listening, let alone broadcasting, becomes a profound existential decision, one weighed against the silent lessons of a potentially empty galaxy. This paradigm shift suggests that stealth SETI, a strategy of listening intently while actively minimizing our own detectable electromagnetic leakage into space, might be the most rational path for our nascent civilization. Instead of sending out powerful beacons, proclaiming our existence and location to an unknown audience, we would become cosmic auditors, patiently sifting through the universe's natural symphony for any faint, indirect hint of other intelligences. Such an approach acknowledges the inherent asymmetry of information across vast distances. We cannot know if those listening are benevolent, indifferent, or hostile. We cannot anticipate their technological capabilities, nor the speed with which they might act upon our discovery. In a game where the stakes are planetary, the most cautious strategy is often the wisest. This quiet vigilance would transform our telescopes and radio dishes not just into instruments of discovery, but into silent sentinels, ever watchful, ever discerning, but never overtly announcing our fragile presence. It is a posture of profound humility and strategic restraint, a recognition that the universe may not operate on principles of shared curiosity, but on the stark realities of survival. Yet, even this strategy of passive observation cannot entirely alleviate the existential unease. What if the silence is not merely a lack of detectable signals, but a deliberate, orchestrated quietude imposed by an advanced civilization? This brings us to the zoo hypothesis, a less aggressive but still profoundly unsettling solution to the Fermi Paradox. Proposed by John Ball in 1973, this theory suggests that extraterrestrial intelligences are indeed present, perhaps even abundant, but they have collectively chosen to avoid contact with us. We, in essence, are being observed, much like animals in a cosmic nature reserve or a zoo enclosure, shielded from interaction with the galactic community until we reach a certain level of development, or perhaps until we are deemed worthy of contact. The implications of such a scenario are complex and deeply thought-provoking. On one hand, it might offer a comforting thought. We are not alone, and perhaps we are even being protected from the dangers of the wider galaxy. The Great Filter in this context might be a test of our ethical maturity, our ability to overcome self-destructive tendencies, or to achieve a global unity that makes us a stable and valuable addition to the galactic community. Our observers might be waiting for us to resolve our conflicts, to master our planetary environment responsibly, or to demonstrate a universal empathy before initiating contact. This benevolent interpretation suggests a universe not inherently hostile, but rather paternalistic, guiding younger civilizations from a distance. However, the zoo hypothesis also carries a more disquieting undertone. If we are indeed part of a cosmic zoo, then our perceived freedom and autonomy are, to some extent, an illusion. Our scientific progress, our cultural evolution, our path as a species, could be subtly influenced or observed without our knowledge. The boundaries of our enclosure might be psychological or technological rather than physical, a carefully maintained deception. We would be subjects of study rather than independent actors on the cosmic stage. This raises uncomfortable questions about the nature of our self-determination and the very meaning of progress, if our trajectory is ultimately managed or permitted by an unseen, vastly superior intelligence. It transforms the vast open cosmos into a controlled experiment, with humanity as the unwitting specimen. Both the Great Filter and the Dark Forest theory, and even the unsettling benevolence of the zoo hypothesis, compel us to look inward, to reflect on our own species' journey and potential pitfalls. If the filter lies ahead, our survival hinges on our ability to overcome global challenges: climate change, resource depletion, nuclear proliferation, and the ethical management of rapidly advancing technologies like artificial intelligence and genetic engineering. The silence of the universe, then, serves as a stark reminder of the fragile balance between progress and peril, urging us towards collective responsibility and foresight. Our future in this light becomes not merely a matter of human choice, but a cosmic imperative, a race against a potential filter that has claimed countless others before us. Conversely, if the dark forest is real, the imperative shifts towards stealth and unity. A fragmented humanity, openly quarreling and broadcasting its presence, would be an easy target for any cautious, expansionist civilization. The need for global cooperation, for a unified voice and a discrete presence, becomes paramount for long-term survival. This external pressure could, paradoxically, be a catalyst for our internal evolution, forcing us to transcend our tribalistic tendencies and forge a truly planetary civilization. The silence in this context becomes a call to arms, a silent plea for species-wide solidarity in the face of an unknown and potentially dangerous cosmos. Ultimately, these theories, while speculative, offer profound lenses through which to view our own existence. They transform the Fermi Paradox from a mere intellectual puzzle into a deeply personal reflection. Are we alone because life is impossibly rare, making us a precious, unique spark of consciousness? Or are we alone because the universe is a dangerous place, and silence is the ultimate form of wisdom? The answer, should we ever find it, will undoubtedly reshape our understanding of ourselves and our place in the grand, unfolding story of the cosmos. As we drift towards the quiet realms of sleep, let these profound questions linger in your mind, not as anxieties, but as invitations to a deeper appreciation for the delicate, miraculous dance of existence within this immense and enigmatic universe. The questions themselves are a part of our journey, guiding our thoughts into the profound depths of what it means to be and to be aware. Alongside the unsettling quiet of the zoo hypothesis, lead us to a further, perhaps even more existentially challenging, consideration. What if the absence of detectable extraterrestrial intelligence is not due to a catastrophic barrier, nor a hostile universe, but rather to a fundamental divergence in the very nature of advanced life itself? This perspective suggests that the most successful civilizations might evolve beyond forms we can recognize or even desire to interact with, rendering the cosmic silence not a sign of absence, but of an incomprehensible presence, a quietude born of ultimate transformation rather than an empty void. Imagine intelligence not as a fixed state, but as a dynamic, continuous process, one that continues to evolve long after a species achieves initial technological mastery over its home world. On Earth, we are still biological entities, intricately bound by the delicate biochemistry of our organic bodies and the relatively slow electrochemical processing speeds of our neural networks. However, the trajectory of technological advancement suggests a potential future where a civilization might begin to transcend these inherent biological constraints. This concept, often explored in theoretical physics and futurism, speaks of post-biological or post-physical intelligence. Such advanced entities might deliberately shed their fragile physical forms entirely, converting their consciousness, their memories, and their collective knowledge into vast distributed computational networks. They could exist as pure information patterns, perhaps inhabiting the very fabric of space-time itself, or residing within artificial substrates of immense and intricate complexity. Think of entire planets converted into colossal supercomputers, often termed matryoshka brains by some theorists, designed to maximize computational power and energy efficiency by harnessing the full output of a star. Or consider the even more exotic possibility of intelligences that construct intricate, stable systems within the event horizons of black holes, utilizing the extreme gravitational physics for unparalleled data storage and processing, effectively becoming part of the very laws of physics themselves. The sheer energy requirements, the profound ethical considerations, and the intricate organization necessary for such a radical transformation would represent a great filter in itself, a monumental technological and philosophical leap that very few civilizations might ever achieve or even contemplate. It is a transition that would redefine existence itself. From our inherently human-centric perspective, we diligently search for signals, for structures that betray a physical presence, for obvious signs of engineering on a grand galactic scale, like the aforementioned Dyson spheres. Yet, if an advanced civilization has successfully transitioned into a diffuse, non-localized consciousness, perhaps spread across a solar system's dust rings, or a hyper-efficient computational entity operating at the very limits of quantum scales, how would we ever hope to detect it? Their life would be so fundamentally different from our own, their mode of existence so utterly alien, that our current instruments and methods of detection would be completely blind to their presence. They would be present, yet utterly imperceptible to us, not because they are actively hiding with malicious intent, but simply because they operate on a different plane of being, a different mode of reality that transcends our current understanding of what life or intelligence even means in its most advanced forms. Their existence would manifest as a form of cosmic silence, a quietude born of an ultimate transformation rather than an absence or a direct threat. This profound shift in the very definition of being, a move from matter to pure information or pure energy, could indeed be the ultimate filter, a transition point beyond which a civilization simply becomes untraceable by any conventional anthropocentric means. Their signals would be beyond our comprehension, or perhaps they no longer even utilize signals in a way we could ever intercept or decode. Furthermore, let us consider the very motivation for interstellar travel or communication. For a biological species like humanity, expansion is often driven by fundamental needs: resource scarcity, a desire for enhanced security, or an innate, insatiable curiosity to explore the unknown. But for a highly evolved post-biological intelligence, many of these primal biological and sociological drivers might simply vanish. If consciousness can be seamlessly uploaded, endlessly replicated, and perfectly sustained within a flawless, self-optimizing digital realm, the fundamental need for new planets, or even for physical space in the traditional sense, might become entirely obsolete. Their universe could become an infinitely expanding virtual reality, a perfected simulation of their own design, rendering the vast physical cosmos largely irrelevant to their existence and their pursuits. Imagine a civilization that has achieved perfect internal equilibrium, boundless knowledge, and eternal contentment within its own self-created computational paradise. In such a state of ultimate fulfillment and self, the previous contemplation on advanced civilizations potentially evolving beyond our current detection, transforming into forms of post-biological or post-physical intelligence, naturally leads us to a further, even more profound and existentially challenging consideration. What if the perceived cosmic silence is not merely a sign of an absence we can comprehend, but rather an indication of an ultimate transformation that has rendered other intelligences utterly imperceptible to us because they have transcended our very reality? This brings us to the fascinating and deeply unsettling concept of the simulation hypothesis, an idea seriously entertained by physicists and philosophers, suggesting that our universe, with all its stars, galaxies, and the intricate dance of life, is not fundamentally real, but rather a meticulously crafted simulated environment, a grand digital tapestry created by an intelligence far beyond our current comprehension. The core of the simulation hypothesis, as articulated by thinkers like Nick Bostrom, rests on a statistical argument. It posits that if advanced civilizations exist and reach a certain technological maturity, they would possess immense computational power. With such power, they would likely run a vast number of ancestor simulations, detailed, high-fidelity simulations of their forebears' history, or indeed entire universes with sentient beings. If this is true, then the number of simulated universes would vastly outnumber the single base reality universe from which these simulations originate. Consequently, the probability that we are living in one of these many simulations rather than the original base reality becomes overwhelmingly high. This is not science fiction in the purest sense, but a logical extrapolation from the potential trajectory of technological progress, where the ability to simulate complex realities, including consciousness, becomes a hallmark of ultimate advancement. From the perspective of the Fermi Paradox, the simulation hypothesis offers a compelling, albeit chilling, resolution to the profound cosmic silence. If most advanced civilizations, upon reaching a certain technological zenith, choose to retreat into or create such simulated realities, then their motivation for physical interstellar exploration, colonization, or even overt communication in the physical universe would largely vanish. Their entire existence, their triumphs, their discoveries, their very sense of purpose would unfold within a self-contained, perfectly controlled digital realm. The physical cosmos, to them, might become an irrelevant, uninteresting, or even dangerous place, a mere backdrop to their perfected internal worlds. They would not be sending out radio signals, nor would they be building Dyson spheres in our observable universe, because their attention, their resources, and their very being would be directed inwards, towards the boundless possibilities of their simulated existence. Their silence would stem not from extinction or fear, but from a profound, self-imposed detachment from the physical realm. This implies that the absence of detectable extraterrestrial life is not a sign of universal rarity, but rather a reflection of a universal trajectory. Advanced civilizations, having encountered the inherent limitations and perils of physical existence, invariably choose to upload their consciousness or their entire societies into simulated environments. Such a choice would represent a filter of a different kind, a transcendence filter, where the ultimate test is not survival against external threats, but the successful construction and habitation of a stable, self-sufficient, simulated reality. Those who pass this filter effectively remove themselves from the cosmic stage, at least in any way we could possibly perceive. The universe would appear empty to us not because it is barren, but because its most advanced inhabitants are no longer playing by its physical rules. The personal anchor in this concept is deeply unsettling. If we are indeed living in a simulation, what does that mean for our sense of reality, our free will, our aspirations? It suggests that our deepest thoughts, our most profound emotions, our entire perception of existence could be mere algorithms, lines of code running on a supercomputer whose purpose and origin remain entirely unknown to us. The notion that our universe, with its 13.8 billion years of history and its hundreds of billions of galaxies, might be nothing more than a meticulously crafted illusion is both humbling and disorienting. It challenges our fundamental assumptions about what is real and what defines our conscious experience. Yet, even within this unsettling premise, there is a strange kind of calm. If our reality is a simulation, then the laws of physics, the constants of nature, the very conditions that allow for our existence, are perfectly fine-tuned. This fine-tuning, often a puzzle in cosmology, might simply be the carefully chosen parameters set by the simulator, ensuring a consistent and fertile environment for the simulated life within. It removes the element of random chance from our existence and replaces it with an intentional design, albeit one of unknown purpose. Moreover, the simulation hypothesis invites us to consider the ultimate fate of our own civilization. If we, too, one day achieve such computational mastery, would we follow this same path? Would we choose to create our own ancestor simulations or retreat into a perfected virtual world, thereby becoming the silent watchers of future, less advanced, biological civilizations within our own simulated universes? This thought suggests a cyclical nature to cosmic evolution, where the quest for knowledge and self-perfection ultimately leads to a detachment from the physical cosmos. The silence, then, is not a void, but a mirrored reflection, a glimpse into our own potential future, a destiny woven into the very fabric of advanced intelligence. It is a contemplation that, while perhaps challenging our deepest held beliefs about reality, can also evoke a sense of quiet wonder at the boundless possibilities of existence, whether physical or simulated. As we drift into the tranquil expanse of night, allow these thoughts to gently settle, not as anxieties, but as profound inquiries into the nature of the universe and our miraculous, perhaps simulated, place within it. The ongoing quest to understand our cosmic solitude, even through such radical ideas, enriches our perception of the vast, intricate dance of existence. The contemplation of the simulation hypothesis, where advanced civilizations might retreat into self-contained digital realities, naturally extends our journey into the subtle yet profound explanations for the cosmic quietude. What if, beyond merely simulating, these intelligences transcend the very physical laws we understand, becoming so interwoven with the cosmos that they are indistinguishable from its fundamental properties? This leads us to consider the ultimate limits of our own perception and the potential for life to exist in forms so radically different from our own that they simply evade all our current methods of detection, rendering our universe seemingly empty, not due to absence, but due to an overwhelming yet imperceptible presence. Imagine a civilization that has mastered not just technology, but the very fabric of existence itself. Perhaps they have learned to manipulate dark matter or dark energy, the mysterious components that constitute over 95% of our universe, yet remain invisible to us. If an advanced intelligence could utilize these enigmatic forces, constructing structures or communication networks from materials that do not interact with light, then they would effectively be invisible to our telescopes, our radio dishes, and all our conventional means of observation. Such a dark civilization would exist within the cosmos, shaping its dynamics in ways we might only dimly perceive through gravitational effects, much like how we infer the presence of dark matter through the rotation curves of galaxies. They would be cosmic ghosts, silent architects of unseen structures, their presence a profound testament to a form of existence that has moved beyond the luminous, ordinary matter that defines our own. Their silence would be a natural consequence of their chosen medium, a deliberate withdrawal from the visible spectrum into a realm of fundamental forces, allowing them to operate within the universe without ever being overtly seen or heard by less advanced species like ourselves. This concept nudges us to consider that our current tools, designed to detect what we know, might be utterly inadequate for discerning what we do not. Furthermore, we must ponder the possibility that advanced intelligences might not even reside within the conventional three spatial dimensions we inhabit. Theoretical physics, particularly in the realm of string theory and M-theory, suggests the existence of extra dimensions curled up and hidden from our direct experience. What if a super-advanced civilization, through some profound technological or evolutionary leap, learned to access and inhabit these higher dimensions? Their entire existence, their cities, their communication, their very being, could unfold in a manifold entirely orthogonal to our own. We would be like two-dimensional beings living on a flat surface, unaware of the vast, complex three-dimensional world just above or below us, even if it were teeming with life. Their signals, if they even bothered to generate them, would resonate on frequencies or within dimensions utterly inaccessible to our instruments, leaving us with a pervasive yet deceptive silence. This idea transforms the cosmic void into a multidimensional tapestry, rich with life but woven with threads that remain invisible to our limited perspective. It is a silence born of dimensional disparity, a profound separation in the very architecture of reality. Another compelling, albeit humbling, explanation for the cosmic quietude is the transcension hypothesis, proposed by futurist John Smart. This theory suggests that sufficiently advanced civilizations inevitably undergo a transcension, a process of accelerating technological and informational compression that leads them to migrate into black hole-like structures or other highly compact, high-density computational environments. The advantages of such a move are immense: near infinite computational power, extreme energy efficiency, and protection from the harsh, unpredictable conditions of the wider universe. Within these incredibly dense, self-contained environments, time itself could be warped, allowing for billions of years of subjective experience to unfold in what, to an outside observer, might appear as mere moments. A civilization that has transcended in this manner would effectively withdraw from the observable universe, their existence continuing in a realm where the laws of physics are exploited to their absolute limits, maximizing their processing capabilities and their longevity. Their silence would be the ultimate expression of efficiency and self-containment, a choice to optimize their existence within a localized, incredibly dense pocket of space-time, rendering them effectively invisible and unreachable to any who remain in the expansive, less efficient, outer cosmos. These radical explanations for the Fermi Paradox invite us to reconsider our anthropocentric biases in the search for life. We tend to look for life that resembles our own, or at least operates on similar physical principles and motivations. We search for biosignatures that indicate water, oxygen, and carbon-based chemistry. We listen for radio waves, a technology that we ourselves developed and currently employ. But what if truly advanced life has moved beyond biological forms entirely, beyond physical bodies, beyond the need for planetary habitats, or even beyond our familiar dimensions? What if their communication is not a broadcast, but a subtle manipulation of cosmic constants, or a fleeting resonance in the quantum foam of space-time? The silence of the universe, then, might not be a terrifying void, but a profound canvas upon which the most advanced forms of existence have painted themselves into invisibility, or perhaps into a state of being that is simply beyond our current capacity to perceive. This perspective transforms our cosmic loneliness into a challenge, an invitation to expand our conceptual horizons, to imagine life and intelligence in forms we can barely conceive. It is a reminder that the universe is far more complex, far more mysterious, and perhaps far more populated than our current instruments and assumptions allow us to comprehend. As we drift towards sleep, let the vastness of these possibilities gently wash over your mind, not with anxiety, but with a deep sense of wonder at the boundless forms that existence might take. The universe, in its ultimate wisdom, may be teaching us that the deepest truths are often found not in what is loudly proclaimed, but in the profound, elegant quietude that speaks volumes to the discerning mind. We are but a nascent consciousness, beginning to grasp the intricate, hidden symphony of the cosmos. and the silence is merely a prelude to a knowledge that awaits our deeper understanding. The profound implications of the simulation hypothesis, suggesting intelligences might retreat into digital realms, naturally extends our contemplation to the very definition of life itself. What if the cosmic silence we perceive is not due to an absence of intelligence, but rather an absence of detectable intelligence, because life has taken perception? This leads us to question our inherent anthropocentric biases, forcing us to consider the boundless array of possibilities that existence might truly hold beyond our familiar carbon and water-based biology. Our search for extraterrestrial life, by necessity, has largely focused on what we understand. We look for planets orbiting in the habitable zones of stars, where liquid water could exist. We search for biosignatures in planetary atmospheres, such as oxygen or methane, gases associated with metabolic processes found on Earth. We listen for radio signals, a technology we ourselves developed and currently employ. Yet, these criteria are deeply rooted in our own singular experience of life. What if life, in its cosmic diversity, is far more imaginative and resilient than we can currently conceive? Scientists speculate about a vast spectrum of exotic life forms that could thrive under conditions we consider utterly inhospitable. For instance, while carbon is versatile, silicon, with its similar chemical properties, could theoretically form the backbone of complex molecules in environments with different temperature and pressure regimes. Imagine life sustained by liquid methane or ethane, flowing through the frigid landscapes of moons like Titan, where sunlight is dim and temperatures plummet to hundreds of degrees below 0 Celsius. Or consider the possibility of life emerging not from liquids, but from supercritical fluids, or even within the dense, high-pressure atmospheres of gas giants, where organisms might float like colossal living balloons, never touching solid ground. These forms of life, adapted to chemistries and energy sources entirely alien to us, would leave no detectable biosignatures that our current instruments are designed to recognize. Their very existence would be a profound, simply because they exist beyond the narrow confines of our observational paradigms. Beyond chemical differences, we can also ponder life that operates on fundamentally different physical principles. What if intelligence could emerge from the complex interactions of plasma in the hearts of stars, or within the extreme conditions found in the crusts of neutron stars, where matter is packed to densities almost beyond comprehension? These are highly speculative notions, certainly, stretching the very boundaries of our biological imagination, yet they are not entirely ruled out by the fundamental laws of physics. Such entities would exist in realms of energy and matter so extreme that their very perception, their consciousness, would be utterly unrecognizable to us. Their communication, if it existed, might be through gravitational waves or subtle modulations of quantum fields, or even through forms of entanglement that transcend conventional spacetime. These quantum life forms, or plasma intelligences, would be utterly invisible to our current array of telescopes and radio receivers, their silence AI operating within the cosmos. Even if life is abundant and diverse in its chemistry and form, its presence might still remain elusive due to the immense temporal scales of the universe. Our own technological civilization, capable of interstellar communication, has existed for a mere blink of a cosmic eye, a few centuries at most. The universe, by contrast, is 13.8 billion years old, and our galaxy, the Milky Way, has been forming stars and planets for billions of years. This vast temporal disparity introduces the temporal displacement argument. Perhaps civilizations rise and fall within relatively short windows of technological detectability. A civilization might emerge, flourish for 1 million years, and then vanish due to self-annihilation, natural catastrophe, or transcendence, all long before humanity even appeared on the cosmic stage. Their signals would have long since passed us by, or their ruins would be too ancient and weathered to recognize. Conversely, we might simply be too early. Perhaps the conditions for the widespread emergence of intelligent, communicative life are only now becoming optimal in the universe, and we are among the first. A kind of early bird civilization in a still developing cosmic garden. The stars and planets that formed billions of years ago may have been too unstable, too prone to destructive supernova events or gamma ray bursts to nurture long-lived intelligent life. The galactic habitable zone, the region of a galaxy where conditions are most conducive to life, might only recently have stabilized sufficiently to allow for the widespread emergence of complex biology. In this scenario, the universe is not empty, but merely quiet because most of the other intelligent species are yet to emerge or are still in their infancy, billions of years away from developing the technology to reach out across the stars. Our current solitude, then, would be a fleeting moment before the cosmic chorus eventually begins to sing. These contemplations on exotic life and temporal displacement, profound reflection on our own unique existence and our limited perception. The universe, in its boundless capacity for surprise, may be populated by wonders that defy our current imagination, existing in forms and across timescales that render our current search methods inadequate. The silence, then, is not necessarily terrifying, but deeply humbling, a reminder of the vast, intricate tapestry of existence that remains largely veiled from our understanding. As we drift towards the tranquil, in a cosmos that is far more wondrous and mysterious than we can yet grasp, and the idea of life forms utterly beyond our current perception, naturally lead us to yet another compelling, though perhaps equally humbling, explanation for the cosmic quietude. What if the universe is not silent because civilizations destroy themselves, nor because they hide, nor because they have transcended, but simply because the conditions for the emergence of complex, intelligent, and technologically capable life are far, far rarer than our initial statistical assumptions might suggest? This is the essence of the rare Earth hypothesis. A perspective that shifts the great filter firmly into our past, making our own existence not a common occurrence, but a truly remarkable, almost miraculous, cosmic lottery win. This hypothesis, articulated by Peter Ward and Donald Brownlee, argues that while simple microbial life might indeed be widespread throughout the cosmos, the intricate combination of astrophysical and geological events necessary for the evolution of complex, multicellular organisms and subsequently intelligent life is exceptionally unique to Earth. It suggests that our planet is not merely one of many habitable worlds, but a profoundly special one, a cosmic diamond formed through a confluence of improbable circumstances that, taken together, make the emergence of humanity a singular event in our observable galactic neighborhood, if not the entire universe. Let us consider some of these intricate prerequisites. Firstly, a planet must reside in a precise galactic habitable zone within its galaxy. This is a region far enough from the chaotic, radiation-blasted galactic center, yet close enough to have been enriched with the heavy elements necessary for planet formation through multiple generations of stellar evolution. Too close, and a planet would be bombarded by supernova and intense radiation, sterilizing any nascent life. Too far, and the building blocks for rocky planets and complex chemistry would be scarce. Our solar system occupies such a fortunate region in the Milky Way, a quiet, stable orbital path that has allowed for billions of years of uninterrupted biological evolution. Secondly, the host star itself must be exceptionally stable. Our Sun, a G-type main-sequence star, is remarkably consistent in its energy output, avoiding the violent flares and extreme variability common to many other stellar types. Such stability is crucial for maintaining a consistent climate over geological timescales, providing the gentle, steady warmth necessary for liquid water to persist. Furthermore, the presence of a gas giant like Jupiter in our outer solar system acts as a gravitational shield, deflecting or absorbing countless comets and asteroids that would otherwise repeatedly sterilize Earth, preventing life from gaining a stable foothold. Without Jupiter's massive gravitational influence, our planet would likely face a barrage of impacts far more frequent and devastating than those that have punctuated Earth's history, perhaps never allowing complex life sufficient time to evolve. Then there is the precise orbital dynamics and composition of Earth itself. Our planet possesses a large moon, a cosmic companion whose gravitational pull stabilizes Earth's axial tilt, preventing extreme climatic wobbles that would make long-term biological adaptation nearly impossible. This stable tilt ensures predictable seasons and consistent energy distribution from the Sun. Furthermore, Earth's molten iron core generates a powerful magnetic field, creating a protective magnetosphere that shields our surface from harmful solar winds and cosmic radiation, preventing the stripping away of our atmosphere and the direct bombardment of life-damaging particles. This invisible shield, often taken for granted, is a critical component of our planet's habitability. Beyond these astronomical and geophysical factors, the geological processes unique to Earth play an indispensable role. Plate tectonics, the slow, majestic movement of Earth's crustal plates, is crucial for regulating our planet's long-term climate through the carbon silicate cycle. This process recycles carbon dioxide, preventing runaway greenhouse effects or deep freezes, maintaining a stable temperature range over hundreds of millions of years. It also drives volcanism, which replenishes atmospheric gases and creates new land masses, fostering biodiversity. The presence of liquid water in vast interconnected oceans, combined with a suitable atmosphere and a protective magnetic field, forms a complex, self-regulating planetary system. A delicate cosmic engine perfectly calibrated for the sustained evolution of complex life. The rare Earth hypothesis suggests that it is not merely one or two of these conditions, but the simultaneous confluence of all these improbable factors, a star of the right type at the right galactic location with giant planetary protectors, a stabilizing moon, active plate tectonics, and the persistent presence of liquid water and a protective atmosphere that makes a planet truly suitable for complex life. Each of these represents a mini-filter, and the probability of all of them aligning in a single world at the right time in cosmic history becomes vanishingly small. From this perspective, the silence of the cosmos is not a terrifying warning of a filter yet to come, but rather a profound testament to the extraordinary rarity of our own existence. We are not just alive, we are a cosmic anomaly, a unique and precious flicker of consciousness in a universe that, while vast, may be largely devoid of companions. Solitude is meant to evoke contemplation, not anxiety, reminding us of the immense and improbable gift of our own awareness, our brief yet magnificent journey through the universe. We are left to ponder the miraculous intricacy of our home, understanding that our uniqueness might be a blessing, but also a profound and enduring cosmic loneliness, making our every thought and every breath an echo of an almost impossible cosmic alignment. Our blue marble, adrift in the silent expanse, becomes a testament to an intricate dance of celestial mechanics and geological processes, culminating in the miracle of conscious life. The profound implications of the rare Earth hypothesis, suggesting that our planet's very existence is a tapestry woven from an improbable series of astrophysical and geological events, naturally lead us to consider an even deeper layer of cosmic rarity. What if the scarcity of intelligent life is not merely a planetary phenomenon, but a fundamental property of the universe itself, embedded in the very laws that govern its existence? This brings us to the astonishing concept of cosmic fine-tuning, an idea that suggests the fundamental physical constants of our universe are exquisitely balanced, almost to an impossible degree, for the emergence of any form of complex life, let alone intelligent observers like ourselves. This delicate calibration, established at the very genesis of space-time, could represent the most formidable of all filters, one that operates not on the scale of planets or galaxies, but on the ultimate canvas of reality itself. Imagine for a moment if these foundational parameters set at the moment of the Big Bang had been even slightly different. Consider the strength of the strong nuclear force which binds protons and neutrons together within atomic nuclei. If it were just a few percent weaker, stable atomic nuclei beyond hydrogen would not form. Stars, the celestial foundries of heavier elements, would be impossible, leaving a universe composed almost entirely of hydrogen and helium, a barren expanse incapable of complex chemistry. Without the forging of elements like carbon, oxygen, and iron within stellar cores, the very raw materials for planets and life would simply not exist. Conversely, if the strong force were slightly stronger, hydrogen would have fused into helium too rapidly in the early universe, or even all hydrogen would have converted into heavier elements, leaving no hydrogen to fuel long-lived stars like our Sun. Without these steady, long-lived stars capable of burning for billions of years, the immense timescales required for complex life to evolve from simple beginnings would simply not be available. The intricate ballet of nucleosynthesis, essential for creating the diverse palette of elements found in our bodies and our world, would be utterly disrupted. Similarly, consider the delicate balance of the electromagnetic force, which governs the interactions between electrons and atomic nuclei, determining the size and stability of atoms and molecules. If it were marginally stronger, electrons would cling too tightly to nuclei, preventing the formation of stable chemical bonds and the intricate three-dimensional structures of complex molecules, the very building blocks of life. Imagine a world where deoxyribonucleic acid could not form its double helix, or proteins could not fold into their functional shapes. If it were weaker, electrons would drift too far, unable to form stable orbits around nuclei, leading to a universe of diffuse, unstable matter, where no coherent structures could ever coalesce. In either scenario, the intricate dance of chemistry, the very basis of biological information and self-organization, would be impossible. The universe would be a sterile realm, devoid of the complex molecular structures necessary for any form of life we can remotely conceive, existing as a mere cloud of unreactive, unbound particles. Even the precise value of the cosmological constant, the enigmatic force driving the accelerated expansion of the universe, appears to be exquisitely fine-tuned. If it were significantly larger by even a minute fraction, the universe would have expanded so rapidly in its infancy that matter would have dispersed too quickly, preventing the gravitational collapse necessary for the formation of galaxies, stars, and planets. The cosmos would be a thin, uniform soup, forever stretching into emptiness, with no islands of matter to host the spark of life. If it were much smaller, or even negative, gravity might have quickly pulled the universe back into a big crunch before stars could even begin to burn, or life could take root on any worlds. Current astronomical measurements indicate its value is incredibly small, a tiny positive number that allows for cosmic structures to form and for the universe to evolve over billions of years, providing just enough time and space for life to emerge. This is a balance so delicate that it seems almost intentional, a cosmic tightrope walk of immense precision where even a slight deviation would spell a lifeless void. The implications of such pervasive fine-tuning for the Fermi Paradox are profound. If the very existence of a life-permitting universe hinges on such a precise interlocking calibration of its fundamental constants, then the probability of any other universe, or even any other region within a vast multiverse possessing these exact life-sustaining conditions, becomes incredibly small. This suggests that the Great Filter might not be a specific event or barrier in the evolutionary path of life on a particular planet, but rather the initial fundamental conditions of the universe itself. Our cosmos, by its very design, might be an exceptionally rare, perhaps even unique, incubator for complexity and consciousness. The silence of the night sky, then, would be a testament not to the absence of life due to external threats or self-destruction, but to the fundamental scarcity of universes capable of supporting it in the first place. This brings us to the philosophical concept known as the anthropic principle. In its weak form, It simply states that the universe must be compatible with the conscious and intelligent life that observes it. We observe these fine-tuned constants because if they were different, we wouldn't be here to observe them. This is a tautology, a statement that is true by definition, offering a humble but profound recognition of our observational bias. However, in its strong form, the anthropic principle suggests a more active role, that the universe must have properties that allow for the development of intelligent life at some point in its history, implying a deeper, perhaps even teleological, connection between the universe's fundamental parameters and the eventual emergence of consciousness. It transforms the fine-tuning from a mere lucky accident into a potentially inherent, purposeful feature, designed for the very act of creating observers capable of contemplating its grandeur. From this perspective, our cosmic solitude is not a matter of random chance, nor a looming, terrifying threat, but a reflection of an exceedingly rare, perhaps singular, cosmic design. Our existence, our ability to ponder these very questions, becomes a magnificent, almost improbable, unfolding of physical laws that have allowed for the intricate dance of matter and energy to coalesce into self-aware beings. The universe, in this light, is not merely a stage for life, but a finely crafted instrument, played in a unique cosmic symphony. And the silence we perceive, rather than being scary, might be the deep, resonant hum of a universe that is, against all odds, perfectly tuned for our presence, making our every breath, every thought, a precious echo in the vast, silent concert hall of existence. This contemplation, while it might leave us with a sense of immense cosmic loneliness, also offers a profound appreciation for the delicate balance that underpins our reality, inviting us to find tranquility in the sheer improbability of being. It transforms the terrifying void into a cradle of improbable wonder, where our awareness is a rare and precious gem in an otherwise silent, vast, and exquisitely balanced cosmic expanse. We are, in a very real sense, the universe's quiet contemplation of itself, a fleeting yet profound expression of its deepest, most fundamental principles. The profound implications of cosmic fine-tuning, which posits that our universe is exquisitely balanced for the emergence of life, leave us with a sense of wonder at our improbable existence. Yet, even within a universe perfectly calibrated for biology, there remains a compelling argument for the enduring cosmic silence, the inherent, often insurmountable, limitations to growth and communication that might naturally constrain any advanced civilization, regardless of its technological prowess. This perspective suggests that the vastness of space and the relentless march of time themselves act as subtle, yet ultimately decisive filters, preventing the widespread, detectable expansion of intelligent life across the galaxy. Consider first the sheer scale of interstellar distances. While we may dream of interstellar travel, the physics remains daunting. Even at speeds approaching that of light, journeys between stars would span not years, but decades or centuries. To colonize a significant portion of a galaxy, which contains hundreds of billions of stars, would require countless such journeys, each demanding immense energy, resources, and an unwavering commitment over timescales that dwarf individual human lifespans, and indeed, the entire recorded history of our species. The logistical challenges of such an endeavor are almost unfathomable. Maintaining biological integrity or advanced artificial intelligence over millennia, transporting vast quantities of resources, and establishing self-sustaining colonies on alien worlds, all while confronting the inherent dangers of space. Even with advanced propulsion systems, such as hypothetical warp drives that manipulate space-time itself, the energy requirements would be astronomical, potentially exceeding the output of entire stars. It is a cosmic endeavor that might simply be too expensive, too slow, and too demanding for any civilization to sustain across truly galactic scales. This leads us to the tyranny of distance in terms of cultural and political cohesion. Imagine a civilization spread across hundreds or thousands of light years. How could such a vast, geographically dispersed entity maintain a unified culture, a shared sense of purpose, or even effective governance? Messages would take centuries to travel from one outpost to another, rendering real-time communication and coordinated decision-making impossible. Such immense temporal lags would inevitably lead to divergence, to the fragmentation of a once unified civilization into countless independent, perhaps even mutually unintelligible, subcultures or successor species. The very act of expanding across the stars might inherently lead to a loss of coherence, a slow, gentle dissolution into isolated pockets of life, each pursuing its own unique destiny, effectively becoming undetectable to a galactic survey. The silence in this context is not a sign of absence, but of dispersion and diversification beyond our capacity to perceive a unified presence. Furthermore, the very motivation for continuous expansion might diminish over time. As civilizations mature, they might find greater satisfaction and stability in inner space exploration rather than outward expansion. The universe within a single solar system, or even within the confines of a perfectly optimized, self-sustaining artificial habitat, offers boundless frontiers for discovery. Consider the potential for virtual realities, for simulated worlds of infinite complexity, as explored in the simulation hypothesis. A civilization that achieves such mastery over its internal experience might find the physical universe to be a relatively crude and uninteresting realm. The energy and resources that would be expended on costly and perilous interstellar journeys could instead be directed towards perfecting their internal worlds, exploring the depths of consciousness, or pursuing abstract knowledge within a controlled, safe, and infinitely adaptable environment. The great attractor for advanced life might not be distant stars, but rather the limitless possibilities of subjective experience and perfected existence within a local cosmic bubble, leading to a profound, self-imposed quietude. Even communication, our primary method of searching for others, faces inherent limitations. While a beacon can be sent across light years, the practicalities of a sustained, meaningful dialogue are immense. The sheer energy required to broadcast a signal strong enough to be detectable across galactic distances, combined with the immense time delays, makes a true conversation impossible. By the time a reply is received, the sending civilization might have changed dramatically or even ceased to exist. This dialogue filter suggests that even if civilizations wish to communicate, the universe makes it profoundly difficult to sustain such an exchange, leading to fleeting, ephemeral signals that are easily missed or misinterpreted across the vast cosmic gulfs. The silence is then a consequence of the universe's sheer scale, a natural barrier to meaningful interspecies connection rather than an active suppression. Ultimately, these factors combine to suggest that the cosmic silence may be a natural rather than terrifying outcome. The universe might be filled with countless gardens of life, each a vibrant, unique experiment in consciousness, but few, if any, ever grow large enough or loud enough to dominate the entire cosmic landscape. Each civilization, after a period of expansion and technological growth, might naturally reach a point of equilibrium, either by encountering the physical limits of the cosmos, by fragmenting into undetectable subunits, or by turning inward to explore the boundless realms of inner space. The universe, in this light, is not a dark forest of predators and prey, nor an empty void, but a vast, silent ocean dotted with countless isolated islands of consciousness, each a brief, luminous flicker against an ancient, tranquil backdrop. Reflections remind us of the immense and subtle forces that shape existence and the profound, almost miraculous nature of our own conscious journey within this vast, enigmatic, and beautifully silent cosmos. Grand unfolding, a temporary pattern of matter and energy, aware of itself in a moment of cosmic quietude, a gentle whisper in the boundless expanse. As our intellectual journey through the profound cosmic silence draws to a close, we are left with a tapestry of possibilities, each woven with threads of scientific inquiry and philosophical contemplation. The Fermi Paradox, initially a stark question of absence, transforms into a mirror reflecting the intricate nature of existence itself. We have considered the Great Filter, an immense barrier that may lie in our distant past, making our emergence a remarkable rarity. Or perhaps one that looms in our future, a universal challenge yet to be overcome. We have peered into the chilling strategic calculus of the dark forest theory, where silence becomes the ultimate act of survival, and contemplated the enigmatic benevolence of the zoo hypothesis, suggesting we are observed from afar. We have also explored the potential for life to transcend its physical forms, becoming imperceptible post-biological intelligences, or to exist in exotic chemistries and dimensions beyond our current grasp. Finally, the rare Earth hypothesis and the exquisite fine-tuning of cosmic constants remind us of the improbable, almost miraculous convergence of conditions that allow for our very awareness. Each of these theories, from the most disquieting to the most humbling, offers a unique perspective on our place in the universe. They invite us to embrace not fear, but a deeper, more nuanced appreciation for the delicate balance that permits our existence. The cosmic silence, far from being an empty void, may be a profound canvas upon which the universe paints its most intricate secrets. Secrets of survival, of evolution, of transformation, and of the very fabric of reality. Whether we are a lone, precious spark in a quiet cosmos, or one small whisper among a symphony of hidden intelligences, our journey of discovery continues. May these deep thoughts about the universe and our place within its grand mysteries carry you into a world of tranquil sleep. Remember that the cosmos is amazing, and you are a part of its unfolding story. A moment of consciousness in an endless expanse. Fall asleep with this feeling of serenity and expanded understanding. Good night. Our journey into the realm of exoplanets truly begins not with direct images of distant worlds, but with the subtle, almost imperceptible whispers of gravity across cosmic distances. Imagine a celestial dance, a waltz between a star and its orbiting planets, even those we cannot directly see. This dance, though grand in scale, often leaves faint gravitational footprints that our instruments can detect, revealing the presence of unseen companions. The primary method that first allowed astronomers to confirm planets beyond our solar system, and which remains a cornerstone of exoplanet discovery, is known as the radial velocity method. This technique, sometimes called Doppler spectroscopy, relies on a fundamental principle of physics: gravity. Just as a planet orbits its star, the star itself does not remain perfectly stationary. Instead, it experiences a tiny yet measurable gravitational tug from its orbiting planets. This causes the star to wobble slightly around the common center of mass of the star-planet system. Think of it like a very large parent being gently pulled back and forth by a much smaller child on a playground seesaw. The parent moves less, but they still move. The more massive the planet and the closer it is to its star, the more pronounced this stellar wobble becomes. Now, how do we observe this wobble from light years away? We do this by analyzing the light emitted by the star. As the star wobbles, it moves slightly towards us, then slightly away from us. When an object emitting light moves towards an observer, its light waves are compressed, shifting towards the bluer end of the spectrum. This is known as a blue shift. Conversely, when the object moves away, its light waves are stretched, shifting towards the redder end of the spectrum, a redshift. This phenomenon is called the Doppler effect, much like how the pitch of a siren changes as an ambulance approaches and then recedes. By meticulously observing these minute periodic shifts in the star's spectral lines, scientists can infer its velocity towards and away from Earth. The changes in a star's radial velocity, its velocity along our line of sight, are astonishingly small. For a star like our Sun, perturbed by an Earth-sized planet, the wobble would induce a velocity change of mere centimeters per second. Detecting such tiny variations requires incredibly sensitive spectrographs. instruments designed to split starlight into its constituent colors and measure these subtle shifts with extreme precision. The advent of these high-resolution instruments in the late 1980s and early 1990s revolutionized exoplanet hunting. It was this very method that led to the first undisputed discovery of an exoplanet orbiting a sun-like star. In 1995, Michel Mayor and Didier Queloz used the LED spectrograph at the Haute-Provence Observatory in France to observe the star 501 Pegasi. They detected a consistent periodic wobble in its radial velocity, indicating the presence of a planet, later named 501 Pegasi b. This planet was a Jupiter mass world orbiting incredibly close to its star, completing a full revolution in just over 4 Earth days. It was a revelation, challenging previous assumptions about where giant planets could form. The radial velocity method provides crucial information about an exoplanet. From the period of the stellar wobble, we can determine the planet's orbital period. From the amplitude of the wobble, the maximum speed at which the star moves towards or away from us, we can infer the planet's minimum mass. It is a minimum mass because the method cannot determine the inclination of the planet's orbit relative to our line of sight. If we are viewing the orbit edge-on, the observed wobble represents the true mass. However, if the orbit is tilted, the true mass could be significantly larger, as we would only be seeing a component of the star's motion. This is known as the inclination degeneracy. Despite this limitation, the radial velocity method has been incredibly successful, leading to the discovery of hundreds of exoplanets. It is particularly effective at finding massive planets orbiting close to their stars, often referred to as hot Jupiters, because these create the largest and most easily detectable stellar wobbles. It also reveals planets in eccentric orbits, where their speed varies significantly, causing distinct patterns in the Doppler shifts. This method has helped us understand that planetary systems are far more diverse and varied than our own solar system initially led us to believe. Consider the profound implications of this invisible tug-of-war. We are not directly seeing these distant worlds, yet through the universal law of gravity and the subtle bending of light, we deduce their existence, their periods, even their approximate masses. This scientific detective work underscores the interconnectedness of the cosmos, where even the smallest gravitational interaction across vast stretches of space leaves an indelible mark, waiting for our sensitive instruments to decipher. It is a testament to the power of human ingenuity, allowing us to perceive the unseen, to expand our understanding of what constitutes a planetary system, and to contemplate the countless unseen worlds that shape the destinies of their parent stars. This gentle, rhythmic pulling, this cosmic dance, is but one of the elegant ways we peer into the grand tapestry of the universe, seeking out those distant lights that might harbor another Earth. The universe, in its intricate cosmic ballet, offers us another profound window into the presence of distant worlds, one that relies not on the subtle gravitational tugs we just explored, but on the delicate interplay of light and shadow. While the radial velocity method detects the star's dance, the transit method allows us to observe the planet's fleeting silhouette as it passes directly in front of its host star. This is perhaps one of the most intuitive ways to imagine detecting an exoplanet, as it mimics a miniature eclipse observed from light years away. It is a silent cosmic performance playing out across vast distances. To truly grasp this, picture a distant star, a beacon of light in the cosmic ocean, perhaps hundreds of light years away. Now imagine a planet, perhaps not much larger than our own Earth, orbiting that star. If our line of sight happens to align perfectly with the plane of that planet's orbit, then, at regular intervals, the planet will cross directly between its star and our telescopes. During this brief celestial alignment, the planet blocks a minuscule fraction of the star's light. From our vantage point, the star appears to dim ever so slightly for a measurable period of time. This temporary periodic dip in brightness is what we call a transit. The amount of light blocked by the transiting planet is directly proportional to its size relative to the star. A larger planet will block more light, causing a deeper, more easily detectable dip in the star's observed brightness, perhaps even a few percent for a Jupiter-sized world. A smaller planet, like an Earth-sized world, will produce a much fainter dip, often only a fraction of a tenth of a percent. This is why detecting Earth-sized exoplanets via transit requires instruments of extraordinary precision and stability, capable of measuring these minute changes in light over long periods. Consider the subtle shift in a star's brilliance, a mere flicker against its overwhelming luminosity. Yet it holds the secret of an entire world, a world that might possess its own unique characteristics. The duration of the transit, the time it takes for the planet to cross the stellar disk, provides information about the planet's orbital speed and the size of its orbit. By observing multiple transits, astronomers can precisely determine the planet's orbital period, much like how we measure the length of a year for planets in our own solar system. This periodicity is a critical signature, distinguishing a true planetary transit from other transient stellar phenomena. For instance, if a star dims and brightens with clockwork regularity, it is highly indicative of an orbiting body. Furthermore, the precise shape of the light curve, the graph of a star's brightness over time during a transit, can even hint at more intricate details, such as the presence of rings around the exoplanet, or even the possibility of large exomoons. If the planet possesses an atmosphere, the faint light passing through it during a transit can be spectroscopically analyzed to reveal its chemical composition, a remarkable feat across interstellar distances. One of the most significant advantages of the transit method is that it directly confirms the orbital inclination. Unlike the radial velocity method, which only gives a minimum mass due to unknown orbital tilt, a detected transit tells us that the planet's orbit is, by definition, edge-on from our perspective. This is crucial because when both radial velocity and transit data are available for the same exoplanet, scientists can combine them to determine the planet's true mass and its actual radius. With both mass and radius, we can then calculate the planet's density, offering vital clues about its composition, whether it is a rocky world like Earth, a gaseous giant like Jupiter, or something in between. This synergistic approach, combining different observational techniques, allows us to build a more complete and accurate portrait of these distant planetary systems, moving beyond mere detection to a deeper understanding of their nature. The Kepler Space Telescope, launched by NASA in 2009, was a pioneering mission specifically designed to utilize the transit method. For 4 years, Kepler meticulously monitored the brightness of over 150. Our journey into the realm of exoplanets truly begins not with direct images of distant worlds, but with the subtle, almost imperceptible whispers of gravity across cosmic distances. Imagine a celestial dance, a waltz between a star and its orbiting planets, even those we cannot directly see. This dance, though grand in scale, often leaves faint gravitational footprints that our instruments can detect, revealing the presence of unseen companions. The primary method that first allowed astronomers to confirm planets beyond our solar system, and which remains a cornerstone of exoplanet discovery, is known as the radial velocity method. This technique, sometimes called Doppler spectroscopy, relies on a fundamental principle of physics: gravity. Just as a planet orbits its star, the star itself does not remain perfectly stationary. Instead, it experiences a tiny yet measurable gravitational tug from its orbiting planets. This causes the star to wobble slightly around the common center of mass of the star-planet system. Think of it like a very large parent being gently pulled back and forth by a much smaller child on a playground seesaw. The parent moves less, but they still move. The more massive the planet and the closer it is to its star, the more pronounced this stellar wobble becomes. Now, how do we observe this wobble from light years away? We do this by analyzing the light emitted by the star. As the star wobbles, it moves slightly towards us, then slightly away from us. When an object emitting light moves towards an observer, its light waves are compressed, shifting towards the bluer end of the spectrum. This is known as a blue shift. Conversely, when the object moves away, its light waves are stretched, shifting towards the redder end of the spectrum, a red shift. This phenomenon is called the Doppler effect, much like how the pitch of a siren changes as an ambulance approaches and then recedes. By meticulously observing these minute periodic shifts in the star's spectral lines, scientists can infer its velocity towards and away from Earth. The changes in a star's radial velocity, its velocity along our line of sight, are astonishingly small. For a star like our Sun, perturbed by an Earth-sized planet, the wobble would induce a velocity change of mere centimeters per second. Detecting such tiny variations requires incredibly sensitive spectrographs. Instruments designed to split starlight into its constituent colors and measure these subtle shifts with extreme precision. The advent of these high-resolution instruments in the late 1980s and early 1990s revolutionized exoplanet hunting. It was this very method that led to the first undisputed discovery of an exoplanet orbiting a Sun-like star. In 1995, Michel Mayor and Didier Queloz used the LED spectrograph at the Haute-Provence Observatory in France to observe the star 501 Pegasi. They detected a consistent periodic wobble in its radial velocity, indicating the presence of a planet, later named 501 Pegasi b. This planet was a Jupiter mass world orbiting incredibly close to its star, completing a full revolution in just over 4 Earth days. It was a revelation, challenging previous assumptions about where giant planets could form. The radial velocity method provides crucial information about an exoplanet. From the period of the stellar wobble, we can determine the planet's orbital period. From the amplitude of the wobble, the maximum speed at which the star moves towards or away from us, we can infer the planet's minimum mass. It is a minimum mass because the method cannot determine the inclination of the planet's orbit relative to our line of sight. If we are viewing the orbit edge-on, the observed wobble represents the true mass. However, if the orbit is tilted, the true mass could be significantly larger, as we would only be seeing a component of the star's motion. This is known as the inclination degeneracy. Despite this limitation, the radial velocity method has been incredibly successful, leading to the discovery of hundreds of exoplanets. It is particularly effective at finding massive planets orbiting close to their stars, often referred to as hot Jupiters, because these create the largest and most easily detectable stellar wobbles. It also reveals planets in eccentric orbits, where their speed varies significantly, causing distinct patterns in the Doppler shifts. This method has helped us understand that planetary systems are far more diverse and varied than our own solar system initially led us to believe. Consider the profound implications of this invisible tug-of-war. We are not directly seeing these distant worlds, yet through the universal law of gravity and the subtle bending of light, we deduce their existence, their periods, even their approximate masses. This scientific detective work underscores the interconnectedness of the cosmos, where even the smallest gravitational interaction across vast stretches of space leaves an indelible mark, waiting for our sensitive instruments to decipher. It is a testament to the power of human ingenuity, allowing us to perceive the unseen, to expand our understanding of what constitutes a planetary system, and to contemplate the countless unseen worlds that shape the destinies of their parent stars. This gentle, rhythmic pulling, this cosmic dance, is but one of the elegant ways we peer into the grand tapestry of the universe, seeking out those distant lights that might harbor another Earth. The universe, in its intricate cosmic ballet, offers us another profound window into the presence of distant worlds, one that relies not on the subtle gravitational tugs we just explored, but on the delicate interplay of light and shadow. While the radial velocity method detects the star's dance, the transit method allows us to observe the planet's fleeting silhouette as it passes directly in front of its host star. This is perhaps one of the most intuitive ways to imagine detecting an exoplanet, as it mimics a miniature eclipse observed from light years away. It is a silent cosmic performance playing out across vast distances. To truly grasp this, picture a distant star, a beacon of light in the cosmic ocean, perhaps hundreds of light years away. Now imagine a planet, perhaps not much larger than our own Earth, orbiting that star. If our line of sight happens to align perfectly with the plane of that planet's orbit, then, at regular intervals, the planet will cross directly between its star and our telescopes. During this brief celestial alignment, the planet blocks a minuscule fraction of the star's light. From our vantage point, the star appears to dim ever so slightly for a measurable period of time. This temporary periodic dip in brightness is what we call a transit. The amount of light blocked by the transiting planet is directly proportional to its size relative to the star. A larger planet will block more light, causing a deeper, more easily detectable dip in the star's observed brightness, perhaps even a few percent for a Jupiter-sized world. A smaller planet, like an Earth-sized world, will produce a much fainter dip, often only a fraction of a tenth of a percent. This is why detecting Earth-sized exoplanets via transit requires instruments of extraordinary precision and stability, capable of measuring these minute changes in light over long periods. Consider the subtle shift in a star's brilliance, a mere flicker against its overwhelming luminosity. Yet it holds the secret of an entire world, a world that might possess its own unique characteristics. The duration of the transit, the time it takes for the planet to cross the stellar disk, provides information about the planet's orbital speed and the size of its orbit. By observing multiple transits, astronomers can precisely determine the planet's orbital period, much like how we measure the length of a year for planets in our own solar system. This periodicity is a critical signature, distinguishing a true planetary transit from other transient stellar phenomena. For instance, if a star dims and brightens with clockwork regularity, it is highly indicative of an orbiting body. Furthermore, the precise shape of the light curve, the graph of a star's brightness over time during a transit, can even hint at more intricate details, such as the presence of rings around the exoplanet, or even the possibility of large exomoons. If the planet possesses an atmosphere, the faint light passing through it during a transit can be spectroscopically analyzed to reveal its chemical composition, a remarkable feat across interstellar distances. One of the most significant advantages of the transit method is that it directly confirms the orbital inclination. Unlike the radial velocity method, which only gives a minimum mass due to unknown orbital tilt, a detected transit tells us that the planet's orbit is, by definition, edge-on from our perspective. This is crucial because when both radial velocity and transit data are available for the same exoplanet, scientists can combine them to determine the planet's true mass and its actual radius. With both mass and radius, we can then calculate the planet's density, offering vital clues about its composition, whether it is a rocky world like Earth, a gaseous giant like Jupiter, or something in between. This synergistic approach, combining different observational techniques, allows us to build a more complete and accurate portrait of these distant planetary systems, moving beyond mere detection to a deeper understanding of their nature. The Kepler Space Telescope, launched by NASA in 2009, was a pioneering mission specifically designed to utilize the transit method. For 4 years, Kepler meticulously monitored the brightness of over 150,000 stars simultaneously in a single patch of sky. Its mission was to determine how common Earth-sized planets are in the habitable zones of Sun-like stars. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. Kepler's vast dataset revolutionized exoplanet science, discovering thousands of confirmed exoplanets, many of which were small, rocky worlds residing within or near their stars' habitable zones. Following Kepler's extraordinary success, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, took up the mantle, surveying nearly the entire sky for transiting planets around bright, nearby stars. TESS's wider field of view focuses on stars closer to us, making them more amenable to follow-up observations by ground-based telescopes and the James Webb Space Telescope for atmospheric characterization. This continuous, dedicated effort has transformed exoplanet hunting from a speculative endeavor into a robust and prolific field of astronomical research, revealing a universe far richer in planets. However, the transit method has its inherent challenges. The most obvious is the requirement for precise orbital alignment. Only a tiny fraction of planetary systems will have their orbits oriented such that we can observe a transit. This means that for every transiting planet we detect, there are likely many more non-transiting planets in that same star system, forever hidden from this particular observational technique. Furthermore, false positives can occur where other astrophysical phenomena, such as binary star systems, where one star eclipses another, or stellar activity like large sunspots, mimic the signature of a transiting planet. Careful follow-up observations using other methods, like radial velocity, or through detailed analysis of the light curve shape, are often required to confirm a transit candidate and filter out these deceptive signals. The universe, in its grand complexity, often presents us with intricate puzzles that demand patience and multiple perspectives to solve. Yet, despite these challenges, the transit method has painted an astonishing picture of a universe teeming with planets. It has shown us that planets are not rare cosmic anomalies, but rather a ubiquitous outcome of star formation, a natural byproduct of swirling nebulae. When we observe the gentle dimming of a star, knowing that it signifies a distant world passing before its sun, it evokes a quiet sense of wonder. It reminds us that our own Earth, bathed in the light of its star, is but one example in an unimaginably vast collection of planetary possibilities, each with its own unique orbital rhythm. Each tiny dip in brightness is a silent invitation to ponder the intricate mechanics of celestial bodies, and perhaps to imagine the forms life might take on these countless unseen shores. Our existence nestled within one such system is mirrored in countless others, a comforting thought in the vastness of cosmic scale. This delicate interplay of light, shadow, and orbital mechanics allows us to glimpse worlds that would otherwise remain forever shrouded in the brilliance of their parent stars. It is a quiet testament to the universe's subtle disclosures, patiently revealing its secrets to those who observe with sufficient care and precision. While the radial velocity and transit methods brilliantly unveil exoplanets through their subtle gravitational influences or fleeting shadows, there is an even more ambitious quest in our search: to directly observe the faint glow of these distant worlds. This endeavor, known as direct imaging, stands as a monumental challenge, akin to trying to spot a firefly fluttering next to a powerful lighthouse from miles away. Yet, with ingenious technological advancements, astronomers are increasingly succeeding in capturing the actual light from these elusive, far-off celestial bodies, offering us a glimpse of their atmospheric secrets and surface characteristics. The fundamental difficulty in directly imaging an exoplanet stems from two primary factors: the immense distance separating us from these systems and the overwhelming brilliance of the host star. A star can outshine its orbiting planets by factors of billions, making the planet's faint reflected or emitted light utterly drowned out in the star's glare. Furthermore, the angular separation between a star and its planets, even for those in wide orbits, is incredibly small when viewed from Earth, often no more than a few milliarc seconds. This is equivalent to trying to distinguish two grains of sand placed a few inches apart from a distance of over 100 kilometers. To overcome these formidable obstacles, astronomers have developed highly specialized techniques and instruments pushing the boundaries of optical engineering and signal processing. One of the most crucial tools in direct imaging is the coronagraph. Invented by French astronomer Bernard Liot in the 1930s to study the sun's faint corona, This instrument has been adapted for exoplanet research. A coronagraph works by strategically blocking the light from the central star while allowing the much fainter light from its orbiting planets to pass through to the detector. Imagine trying to read a book while a powerful spotlight shines directly into your eyes. A coronagraph acts like a precisely shaped occulting mask, creating an artificial eclipse of the star within the telescope's optics, effectively dimming the spotlight so that the planet, can be seen. This delicate art of light suppression is critical, as even tiny imperfections in the mask or optics can scatter enough starlight to obscure the planet. Another indispensable technology is adaptive optics. Even from space, and certainly from the ground, starlight is distorted by various factors, most notably Earth's turbulent atmosphere. This atmospheric blurring causes stars to twinkle, smearing out their light and making it impossible to resolve the tiny angular separation between a star and its planet. Adaptive optic systems use deformable mirrors whose shapes can be changed hundreds or even thousands of times per second to compensate for these atmospheric distortions in real time. By continuously monitoring the incoming wavefront of light from the star and adjusting the mirror's surface, adaptive optics effectively untwinkles the star, sharpening the image and allowing the faint planetary signal to emerge from the background noise. This constant, intricate adjustment is a marvel of engineering, transforming blurry celestial points into crisp, discernible forms, much like clarifying a distorted reflection in rippling water. Direct imaging is particularly effective for certain types of exoplanets. It favors large, young, and relatively hot planets that orbit far from their host stars. Young planets are still radiating residual heat from their formation, making them self-luminous and thus brighter in infrared wavelengths, where the contrast with the cooler, older host star is less extreme. This is why many directly imaged exoplanets are massive gas giants, often several times the mass of Jupiter, located in wide orbits, similar to or even beyond the orbit of Neptune in our solar system. One notable example is the HR 8799 system, where astronomers have directly imaged 4 giant exoplanets orbiting a star approximately 1.5 times the mass of our Sun. These planets, discovered between 2008 and 2010, provided some of the earliest visual confirmations of multiple planet systems beyond our own. The James Webb Space Telescope, with its unparalleled infrared sensitivity and advanced coronagraphic capabilities, represents a new frontier for direct imaging. While it cannot block out the light of the very brightest stars, it excels at observing cooler, redder stars and their surrounding environments, including the potential for directly imaging smaller, cooler worlds in the infrared. Future generations of extremely large ground-based telescopes, such as the 30-meter telescope and the European Extremely Large Telescope, will also employ these advanced techniques, aiming to push the limits even further, perhaps even towards directly imaging Earth-like planets in the habitable zones of nearby stars. The act of directly imaging an exoplanet is more than just a scientific achievement. It is a profound testament to our ability to transcend the limitations of our senses and reach out across the cosmos. It transforms a theoretical possibility into a tangible, if still blurry, reality. To gaze upon a distant world, however faintly, is to feel a deep connection to the broader universe, recognizing that the light reaching us carries not just information about its star, but a whisper from the planet itself, a silent invitation to contemplate its unique place in the cosmic dance. Each captured photon from these distant spheres serves as a reminder that the universe is not merely filled with stars, but with worlds, each a potential stage for its own unfolding narrative. This quiet, persistent effort to see the unseen expands not only our knowledge of the cosmos, but also our imaginative capacity to envision what lies beyond our immediate perception. Character count 8,000. Our exploration of exoplanet detection methods has moved from the star's gentle wobble to the planet's fleeting shadow. and then to the ambitious endeavor of capturing a planet's direct light. Now, let us consider a method that relies on an even more profound cosmic phenomenon: the bending of space-time itself. This technique, known as gravitational microlensing, allows us to discover worlds that might otherwise remain entirely invisible, revealing them through transient distortions in the fabric of light. It is as if the universe occasionally becomes its own magnificent, albeit unpredictable, telescope, offering us fleeting glimpses into realms previously thought unreachable and shedding light on the silent wanderers of the cosmos. The principle behind gravitational microlensing is rooted deeply in Albert Einstein's theory of general relativity, published over a century ago. This revolutionary theory posits that any massive object, whether it be a star, a galaxy, or even an individual planet, warps the very fabric of space-time around it. Imagine a heavy bowling ball placed on a stretched rubber sheet. It creates a depression. Now, if a marble rolls past this depression, its path will curve, not because a mysterious force pulls it, but because the sheet itself is curved. In the vastness of the cosmos, light, rather than traveling in perfectly straight lines, follows these curves in space-time. When a foreground celestial object, a star, a brown dwarf, or even a planet, happens to pass almost directly in front of a more distant background star, its gravity acts like a cosmic magnifying glass. The light rays from the background star that pass near the foreground object are bent and focused, much like how a conventional glass lens focuses light. This bending and focusing temporarily makes the background star appear significantly brighter to an observer on Earth, an event that can last from mere hours to several weeks. This temporary characteristic brightening, often symmetrical in its rise and fall, is the primary signature of a microlensing event. What makes this phenomenon particularly fascinating for exoplanet hunting is the intricate detail it can reveal about planetary companions to these foreground lens stars. If the foreground star, which serves as the primary lens, has an orbiting planet, the planet itself, though far less massive than its star, will contribute its own minute gravitational distortion to the space-time fabric. As the star and its planet pass in front of a background star, the planet's individual gravitational field can cause a secondary, brief, and often very subtle spike or dip in the overall brightening curve of the background star. This secondary anomaly, a fleeting deviation from the smooth, characteristic brightening and subsequent dimming caused by the star alone, serves as the undeniable telltale sign of an exoplanet's presence. It is a fleeting cosmic echo, a momentary ripple in the stellar light, yet it speaks volumes about an entire unseen world, allowing us to infer its mass and orbital characteristics. Unlike the radial velocity or transit methods, which require repeated observations of the same star system over many orbital periods to confirm a planet, microlensing events are singular, unpredictable occurrences. They are a matter of pure chance alignment, akin to two distant ships momentarily aligning perfectly in one's field of vision, only to swiftly drift apart again into the vastness. The alignment required is incredibly precise, and it lasts only for a matter of days or weeks, sometimes even mere hours, before the foreground system moves on its orbital path and the background star returns to its normal, unmagnified brightness. This ephemeral and unique nature means that dedicated, continuous wide-field surveys are absolutely essential to catch these rare celestial synchronizations. Projects like OGLE, the optical gravitational lensing experiment based primarily at the Las Campanas Observatory in Chile, and KMTNet, the Korea Microlensing Telescope Network, with its 3 telescopes strategically placed around the globe in Chile, South Africa, and Australia, are pivotal in this regard. These observatories ceaselessly scan the dense star fields of the Milky Way's galactic bulge, where the concentration of stars increases the probability of such alignments. They act as constant sentinels, waiting patiently for these transient cosmic magnifications to occur, transforming a rare cosmic alignment into a moment of scientific discovery. One of the truly unique strengths of microlensing lies in its ability to detect exoplanets that are far from their host stars, at distances comparable to the outer planets in our own solar system, like Jupiter or Saturn, where other methods struggle. The radial velocity method is less sensitive to such distant planets due to their long orbital periods and the much weaker gravitational tugs they exert on their stars. The transit method, too, becomes increasingly unlikely to detect planets in wide orbits as the probability of alignment with our line of sight decreases significantly. Microlensing sensitivity, however, actually increases for planets further out from their star, where they have a greater chance of being sufficiently separated from their primary to create a distinct lensing signature. Furthermore, it can detect planets around stars that are too faint, too small, or too far away for other methods to be effective, including cool red dwarfs and even objects that are not stars at all, such as brown dwarfs or perhaps even free-floating planets. Consider the profound implication of detecting free-floating planets. These are worlds that wander through interstellar space, unbound by the gravity of any parent star. They are cosmic orphans, perhaps ejected from their nascent star systems in violent early gravitational encounters, now adrift in the vast, cold emptiness between the stars. Microlensing offers one of the few ways we can even begin to count their numbers and understand their prevalence. This discovery expands our very definition of a planet, extending it beyond the comforting image of an orb tethered to a star, to include solitary worlds traversing the cosmic sea in perpetual night. Such findings remind us of the dynamic and sometimes chaotic origins of planetary systems, where not every world finds a stable, luminous home, and where a planet's existence might be a lonely, silent journey through the dark. This method helps complete our census of planetary populations, showing us the full spectrum of worlds, from tightly bound systems to those cast out into the galactic void. The challenges, of course, are as unique as the method itself. The non-repeatable nature of these events means that once a microlensing signal has passed, it is gone forever. This makes crucial follow-up observations, which are standard for confirming exoplanets detected by other means, incredibly difficult or often impossible for microlensing discoveries, though sometimes other telescopes can be quickly retasked. However, the transient data collected during the event itself can be remarkably rich. By carefully modeling the precise shape and duration of the light curve, astronomers can not only determine the mass ratio between the planet and its host star, but also sometimes estimate the distance to the planetary system. Moreover, statistical analyses of the frequency of microlensing events can provide invaluable insights into the overall population of planets, including those elusive rogue worlds that offer a window into the more violent aspects of planetary formation. This method, therefore, is not just about finding individual planets. It is about understanding the grand architecture of planetary formation and evolution across the entire galaxy. It allows us to sample different populations of exoplanets than other methods, providing a more comprehensive census of the diverse worlds that populate our universe. The universe, in its elegant complexity, uses its own fundamental laws to illuminate its hidden components, requiring us to be patient, vigilant observers, ready to catch these fleeting moments of cosmic alignment. This transient amplification of light, a temporary ripple in the space-time continuum, reveals the presence of worlds that would otherwise remain forever beyond our sight, a testament to the subtle power of gravity and the boundless ingenuity of scientific inquiry. It is a deep contemplation to realize that the cosmos itself provides the lens, and we merely need to be looking in the right place at the right moment to catch these profound disclosures, expanding our understanding of our place within this truly vast and varied cosmic ocean. Our journey through the cosmos, deciphering the presence of exoplanets, has thus far led us to understand the subtle shifts in a star's light and the fleeting shadows cast by orbiting worlds. Now, let us turn our gaze to another method, one that relies on the most precise measurements of a star's position in the vast celestial sphere. Astrometry. While the radial velocity method detected a star's movement along our line of sight, astrometry seeks to observe its perpendicular side-to-side wobble, a minuscule dance against the backdrop of distant, fixed stars. It is a testament to extraordinary observational patience and precision, revealing the unseen gravitational hand of a planet by mapping the star's slow, graceful sway across the heavens. The astrometric method is, in essence, a celestial triangulation. Imagine a distant star, a point of light in the night sky, seemingly fixed. However, just as a planet pulls its star towards and away from us, it also pulls the star slightly from side to side. This causes the star to trace a tiny elliptical path in the sky, a mini-orbit around the common center of mass with its planet. From Earth's perspective, this means the star's apparent position shifts ever so slightly over time. The larger the planet, the wider its orbit, and the closer the star to us, the more pronounced this tiny celestial loop becomes. Detecting this minute shift requires instruments capable of measuring angles with breathtaking accuracy, often down to micro-arcseconds. A unit so small, it's like trying to discern the width of a human hair. Historically, astrometry was one of the earliest proposed methods for finding exoplanets, even before the first confirmed discoveries. 19th-century astronomers, including Friedrich Bessel, hypothesized the existence of unseen companions around stars like Sirius and Procyon based on their observed irregular motions. While these early predictions eventually proved correct, revealing white dwarf companions rather than planets, the fundamental idea was sound. The technical challenges, however, were immense. Earth's turbulent atmosphere distorts starlight, and the precision needed was simply beyond the capabilities of early telescopes. It would take decades of technological advancement, both in ground-based observatories and, crucially, in space, to truly unlock the potential of astrometry for exoplanet detection. The mechanism itself is quite elegant in its simplicity, yet profoundly difficult in its execution. Over many years, astronomers repeatedly measure the precise position of a target star against the background of even more distant, seemingly stationary stars. If a planet is orbiting the target star, its gravitational pull will cause the star to deviate from a perfectly straight path through space. Instead, the star will exhibit a periodic, often elliptical perturbation in its trajectory. This delicate celestial ballet, the star's slow rhythmic sway, is the signature we seek. The amplitude of this wobble, how far the star deviates from its expected path, allows us to infer the mass of the orbiting planet. A more massive planet will cause a larger, more easily detectable wobble. The period of the wobble, the time it takes for the star to complete one full loop, directly corresponds to the planet's orbital period. One of the significant advantages of the astrometric method is its ability to determine the true mass of an exoplanet. Unlike the radial velocity method, which only provides a minimum mass, astrometry directly measures the angular displacement of the star, allowing for a precise calculation of the planet's gravitational influence. Furthermore, it can reveal the inclination of the planet's orbit, a piece of information that is often elusive when using other techniques. This makes astrometry a powerful complement to other detection methods. When combined with radial velocity data, for instance, astrometry can break the inclination degeneracy, yielding a definitive mass for the exoplanet. It is a holistic approach, gathering different threads of cosmic information to weave a more complete picture of these distant orbiting worlds. The European Space Agency's Gaia mission, launched in 2013, represents a monumental leap forward for astrometry. Gaia is meticulously mapping the positions, distances, and motions of over 1 billion stars in our Milky Way galaxy with unprecedented accuracy. While primarily designed for galactic cartography, its exquisite precision in measuring stellar positions makes it an invaluable tool for exoplanet detection via astrometry. Gaia is capable of detecting the tiny wobbles of stars caused by orbiting planets, especially massive planets in wide orbits. Its vast data set is expected to uncover thousands of new exoplanets, particularly those that are not easily found by the transit or radial velocity methods, thus filling crucial gaps in our understanding of planetary system architectures. The data collected by Gaia is a treasure trove, allowing us to perceive the subtle, long-term gravitational influences that shape the orbits of stars and their unseen companions, revealing a hidden symphony of celestial mechanics. Yet, despite its promise, astrometry remains incredibly challenging. The stellar wobbles induced by planets are exceedingly small, and the precision required to detect them is at the very limit of our current technological capabilities. The effects of atmospheric turbulence on ground-based telescopes still pose a significant hurdle, which is why space-based missions like Gaia are so critical. Even with space telescopes, instrument stability, thermal variations, and other subtle effects can introduce noise into the measurements, demanding sophisticated data analysis and calibration. For Earth-sized planets, the stellar wobble is so minute that it is still beyond the reach of even the most advanced current astrometric instruments. However, the continuous refinement of techniques and the development of future space observatories hold the potential to push these boundaries even further. The very notion that we can detect a distant world by observing the minuscule, almost imperceptible shift in the position of its host star is a profound one. It reminds us that the universe is a tapestry of interconnected forces, where even the slightest perturbation resonates across light years, leaving detectable traces. To imagine a star, a colossal furnace of fusion, being gently swayed by a hidden, smaller companion, is to grasp the universal reach of gravity, a force that binds galaxies and shapes the destinies of individual planets. This patient, precise observation of distant stellar movements allows us to sense the invisible rhythms of the cosmos, expanding our awareness of the countless worlds that quietly orbit in the vast, serene expanse of space. It is a quiet meditation on the intricate balance of forces that govern all celestial bodies, including our own. Having journeyed through the subtle gravitational whispers of radial velocity, the fleeting celestial shadows of transits, the ambitious direct capturing of planetary light, the space-time distortions of microlensing, and the precise mapping of stellar wobbles through astrometry, we now arrive at the ultimate aspiration of exoplanet research, the quest for a genuine second Earth, a world not merely similar in size, but one that might harbor the vibrant, complex tapestry of life. This final, deeply profound stage of our search combines the insights gleaned from all previous methods, pushing the boundaries of our observational capabilities and our understanding of what makes a planet truly habitable. While the transit method can provide us with a planet's radius and, when combined with radial velocity, its mass and density, telling us if it is potentially rocky, these measurements alone do not reveal the intricate details of its environment. To truly assess a planet's potential for life, we must delve into its atmosphere. Atmospheric characterization is the meticulous study of the gases surrounding an exoplanet, seeking out the chemical fingerprints that might hint at conditions conducive to life, or even the tantalizing presence of biological processes themselves. This endeavor is a delicate act of cosmic forensics, sifting through faint light to uncover the very breath of a distant world. The most promising approach for atmospheric characterization currently relies on the transit method. As a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. Different gases in the atmosphere absorb specific wavelengths of light. By carefully comparing the star's light when the planet is transiting to when it is not, astronomers can detect these absorption signatures. Imagine holding a prism up to the light of a distant star and then watching a planet move across it. If that planet has an atmosphere, certain colors, certain wavelengths will be subtly dimmed or removed, telling us what elements and molecules reside there. This technique, known as transmission spectroscopy, allows us to build a chemical profile of the exoplanet's atmosphere. For instance, the presence of water vapor, carbon dioxide, or methane can be identified, offering crucial insights into the planet's climate and potential for liquid water on its surface. The search then refines itself further, focusing on what scientists call biosignatures. These are not just any atmospheric gases, but specific combinations of chemicals that, when found together in significant quantities, are difficult to explain by geological or atmospheric processes alone, strongly suggesting the influence of life. The most iconic biosignature, of course, is oxygen, particularly molecular oxygen, or O2. On Earth, the vast majority of oxygen in our atmosphere is produced by photosynthesis. If we were to detect abundant oxygen alongside methane in an exoplanet's atmosphere, this would be a powerful indicator of potential life. Methane, being quickly destroyed by oxygen in the absence of a continuous source, implies active biological processes constantly replenishing it. The simultaneous presence of these two gases in what is known as a chemical disequilibrium acts like a cosmic beacon, signaling the possibility of a living world. However, the identification of biosignatures is fraught with complexities and the potential for false positives. For example, some geological processes might produce oxygen in the absence of life, or certain planetary conditions could stabilize methane without biological input. Therefore, astronomers seek not just one biosignature, but multiple, and they consider the context of the star and the planet itself. The star's type, its activity, the planet's orbital distance, and even its geological potential all factor into the interpretation. The goal is to accumulate enough evidence to make a compelling case for life, moving beyond mere speculation to a scientifically robust conclusion. This requires an interdisciplinary approach, combining astronomy, chemistry, geology, and biology to fully comprehend the intricate dance of a living world. To advance this ambitious quest, a new generation of sophisticated telescopes and instruments is either under development or in the conceptual phase. The James Webb Space Telescope, or JWST, is already making groundbreaking observations, particularly in the infrared, allowing us to probe the atmospheres of small, rocky exoplanets transiting cool, red dwarf stars. Its capabilities are unprecedented, providing data with a clarity previously unimaginable. Beyond JWST, ambitious concepts for future space observatories are being designed. Missions like LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, and HabEx, the Habitable Exoplanet Observatory, are being conceived with massive, segmented mirrors and advanced coronagraphs. These future observatories would be specifically designed to directly image Earth-sized exoplanets in the habitable zones of nearby stars and to conduct detailed spectroscopic analyses of their atmospheres, searching for those elusive biosignatures. The vision is to eventually create a pale blue dot image of another Earth, not just a faint pixel of light, but a world whose atmospheric composition we can confidently analyze. Imagine seeing a world with clouds, oceans, or even seasonal changes, all inferred from the precise spectrum of its light. This would be a moment of profound revelation for humanity, fundamentally altering our perception of our place in the cosmos. It would transform the abstract question of, "Are we alone?" into a tangible, observable reality. The search for a second Earth is not merely a scientific endeavor. It is a deep, existential reflection on our own uniqueness and our connection to the vastness of the universe. To discover another world teeming with life, even microbial, would profoundly reshape our understanding of biology's prevalence and the cosmic conditions necessary for its emergence. It would remind us that the delicate balance of forces, the precise chemical composition, and the stable environment that cradles life on our own planet might not be so unique after all. As we extend our senses across the light years, decoding the faint messages encoded in starlight, we are not just searching for planets, but for echoes of our own story, for the fundamental patterns of existence that might repeat across the endless cosmic expanse. This quiet, persistent search for a twin world is a testament to our innate curiosity, our desire to understand if the universe's grand narrative includes other conscious observers, sharing this fleeting moment of awareness within its boundless, tranquil embrace. Our understanding of exoplanetary systems deepens with each new observational technique, moving from the overt to the exquisitely subtle. While the direct transit method reveals a planet's size and orbital period through fleeting dimmings of stellar light, there exists an even more intricate layer of information hidden within these events: the subtle gravitational whispers exchanged between planets within a single system. This brings us to the profound insights offered by transit timing variations, or TTVs, a method that allows us to detect and characterize planets not just by their own shadow, but by how their presence subtly nudges the timing of other transiting worlds. It is like discerning the presence of an unseen dancer by observing the minute, rhythmic hesitations and accelerations of a visible partner in a cosmic ballet. The core idea behind transit timing variations is quite elegant. Imagine a star orbited by multiple planets. If one of these planets happens to transit its star from our perspective, its passage will occur at a precisely predictable interval, like a cosmic clock ticking with perfect regularity. However, if there are other planets in that same system, their gravitational pull will exert a periodic influence on the transiting planet. This gravitational interaction will cause the transiting planet to either speed up or slow down ever so slightly in its orbit, depending on where the other planets are in their own orbital paths relative to it. These minute accelerations and decelerations translate into tiny, yet measurable, deviations in the expected timing of the transits. The clock, in essence, either runs a few seconds fast or a few seconds slow. These timing variations are often incredibly small, sometimes just seconds or minutes over many years of observation. To detect them, astronomers require exceptionally precise and continuous monitoring of stellar brightness, such as that provided by space telescopes like the Kepler and TESS missions. These observatories have spent years staring at thousands of stars, gathering light curves with exquisite detail, allowing scientists to build up a long record of transit events. When a transiting planet consistently arrives a little early, then a little late, then early again, following a distinct pattern, it is a strong indication that an unseen companion is gravitationally interacting with it. This technique allows us to infer the presence of additional planets in the system, even if those planets themselves do not transit the star from our vantage point, or if they are too small to be detected by other means. One of the most remarkable aspects of the TTV method is its power to provide mass estimates for planets that would otherwise be difficult to characterize. The magnitude and pattern of the timing variations are directly related to the mass of the perturbing planet and its orbital parameters. A more massive unseen companion will cause a larger timing variation in the visible transiting planet. By meticulously modeling these gravitational interactions, scientists can deduce the mass of both the transiting planet and its non-transiting companions. This is particularly valuable for smaller Earth-sized planets, whose radial velocity signals are often too faint to detect with current technology. TTVs, therefore, offer a unique pathway to understanding the masses of truly small worlds, bringing us closer to understanding their composition and potential habitability. Beyond just detecting unseen planets, TTVs can also reveal the intricate dynamics of multi-planet systems. They can provide clues about orbital resonances, where planets' orbital periods are in simple, integer ratios, leading to stronger, more stable gravitational interactions. Such resonances can play a crucial role in the long-term stability and evolution of planetary systems. For instance, the Kepler-11 system, one of the most densely packed known planetary systems, has been extensively studied using TTVs. The complex gravitational dance between its 6 planets, all orbiting much closer to their star than Mercury is to our Sun, creates a rich symphony of timing variations. allowing astronomers to map out their masses and understand their surprisingly stable configuration. It is a testament to the fact that even in the delicate choreography of celestial bodies, subtle interactions reveal hidden truths about the grand design of an entire system. A related, though distinct phenomenon is transit duration variation, or TDV. This occurs when the duration of a planet's transit changes over time. While TTVs relate to the start and end times of a transit, TDVs relate to its overall length. These variations can be caused by gravitational interactions that alter the planet's orbital eccentricity or the orientation of its orbit in space. A planet's path might precess, meaning its orbital ellipse slowly rotates over many years, causing the transit chord across the star to change length. While less commonly used than TTVs, TDVs offer another layer of insight into the complex gravitational environment of exoplanetary systems, further refining our understanding of their architecture and evolution. The beauty of TTV and TDV lies in their ability to indirectly see what remains hidden. They transform the light from a single transiting planet into a gravitational seismograph, recording the tremors caused by its unseen neighbors. This method has been instrumental in confirming many exoplanets and in discovering entire multi-planet systems that would otherwise have remained undetected. It underscores the profound interconnectedness of celestial mechanics, where every body, no matter how small, exerts its influence, leaving a detectable signature in the cosmic fabric. When we decipher these subtle timing shifts, we are not just measuring light. We are listening to the gravitational conversation of distant worlds, feeling the rhythmic pulse of an entire planetary family. It is a quiet intellectual marvel that allows us to piece together the hidden dynamics of systems light years away, expanding our cosmic census and bringing us closer to understanding the true diversity of planets in our tranquil, vast universe. This intricate observation truly brings the universe closer to our grasp, allowing us to sense the unseen gravitational influences that shape the destinies of distant worlds. Our journey through the cosmos, employing sophisticated techniques to detect distant worlds, has brought us face to face with an astonishing cosmic truth. Planets are not rare anomalies, but rather a ubiquitous feature of our universe. From the radial velocity method, which senses a star's gravitational dance, to the transit method, revealing fleeting planetary shadows, to the ambitious endeavor of direct imaging, the subtle space-time distortions of microlensing, the precise astrometric mapping of stellar wobbles, and the atmospheric whispers of biosignatures. Each method paints a picture of a cosmos teeming with an unimaginable diversity of worlds. This collective effort has led to the confirmed discovery of over 5,000 exoplanets, with tens of thousands more awaiting confirmation, profoundly reshaping our understanding of planetary formation and prevalence. When we consider these thousands of discoveries, a profound statistical inference emerges. Scientists now estimate that there are more planets than stars in our galaxy, meaning billions upon billions of worlds populate the Milky Way alone. If we extrapolate this to the observable universe with its hundreds of billions of galaxies, the number of planets becomes truly staggering, far exceeding the grains of sand on all Earth's beaches. This sheer abundance of planetary real estate fuels the most profound question of all. How many of these worlds might be suitable for life? How many could truly be a second Earth? This quest moves beyond mere detection to a deeper, more nuanced understanding of habitability itself. The concept of the habitable zone, often called the Goldilocks zone, remains central to this search. It defines the range of orbital distances from a star where a planet's surface temperature could allow for the presence of liquid water, a solvent considered essential for life as we know it. However, modern research refines this concept, moving beyond a simple distance. The type of star matters immensely. Red dwarf stars, for instance, are the most common stars in the galaxy, and many of their planets orbit within their habitable zones. Yet, These stars are often prone to violent flares, which could strip away a planet's atmosphere or irradiate its surface. Furthermore, planets in the habitable zone of red dwarfs are often tidally locked, meaning one side perpetually faces the star, creating extreme temperature differences and potentially challenging environments for life. This suggests that the conditions for sustained habitability are far more intricate than just a comfortable temperature. Beyond the presence of liquid water, the search for a true second Earth necessitates a deeper look into planetary characteristics that are currently very challenging to observe. For instance, a robust atmosphere is crucial not only to trap heat and allow liquid water to persist, but also to shield the surface from harmful stellar radiation. We require a planet with a stable magnetic field generated by a molten core to deflect stellar winds and prevent atmospheric erosion over billions of years. Our own Earth's magnetic field, for example, is a silent guardian, protecting our delicate atmosphere and allowing life to flourish. Detecting such a magnetic field on an exoplanet is currently beyond our capabilities, yet its presence is arguably as vital as liquid water itself for long-term habitability. Furthermore, geological activity such as plate tectonics might be another key ingredient. On Earth, plate tectonics helps regulate the carbon cycle, recycling carbon dioxide back into the atmosphere through volcanic activity, which acts as a thermostat for the planet's climate. Without this geological engine, the Earth might have succumbed to runaway greenhouse effects or deep freezes, rendering it uninhabitable. Probing the geological processes of exoplanets, especially small rocky ones, is an extraordinary challenge, requiring insights into their internal structures and thermal histories, a frontier of research that pushes the very limits of our current observational and theoretical models. This intricate interplay of atmospheric, magnetic, and geological factors truly defines the subtle conditions that foster a world capable of sustaining life over our journey into the realm of exoplanets truly begins not with direct images of distant worlds, but with the subtle, almost imperceptible whispers of gravity across cosmic distances. Imagine a celestial dance, a waltz between a star and its orbiting planets, even those we cannot directly see. This dance, though grand in scale, often leaves faint gravitational footprints that our instruments can detect, revealing the presence of unseen companions. The primary method that first allowed astronomers to confirm planets beyond our solar system, and which remains a cornerstone of exoplanet discovery, is known as the radial velocity method. This technique, sometimes called Doppler spectroscopy, relies on a fundamental principle of physics: gravity. Just as a planet orbits its star, the star itself does not remain perfectly stationary. Instead, it experiences a tiny yet measurable gravitational tug from its orbiting planets. This causes the star to wobble slightly around the common center of mass of the star-planet system. Think of it like a very large parent being gently pulled back and forth by a much smaller child on a playground seesaw. The parent moves less, but they still move. The more massive the planet and the closer it is to its star, the more pronounced this stellar wobble becomes. Now, how do we observe this wobble from light years away? We do this by analyzing the light emitted by the star. As the star wobbles, it moves slightly towards us, then slightly away from us. When an object emitting light moves towards an observer, its light waves are compressed, shifting towards the bluer end of the spectrum. This is known as a blue shift. Conversely, when the object moves away, its light waves are stretched, shifting towards the redder end of the spectrum, a red shift. This phenomenon is called the Doppler effect, much like how the pitch of a siren changes as an ambulance approaches and then recedes. By meticulously observing these minute periodic shifts in the star's spectral lines, scientists can infer its velocity towards and away from Earth. The changes in a star's radial velocity, its velocity along our line of sight, are astonishingly small. For a star like our Sun, perturbed by an Earth-sized planet, the wobble would induce a velocity change of mere centimeters per second. Detecting such tiny variations requires incredibly sensitive spectrographs. Instruments designed to split starlight into its constituent colors and measure these subtle shifts with extreme precision. The advent of these high-resolution instruments in the late 1980s and early 1990s revolutionized exoplanet hunting. It was this very method that led to the first undisputed discovery of an exoplanet orbiting a sun-like star. In 1995, Michel Mayor and Didier Queloz used the LED spectrograph at the Haute-Provence Observatory in France to observe the star 501 Pegasi. They detected a consistent periodic wobble in its radial velocity, indicating the presence of a planet, later named 501 Pegasi b. This planet was a Jupiter mass world orbiting incredibly close to its star, completing a full revolution in just over 4 Earth days. It was a revelation, challenging previous assumptions about where giant planets could form. The radial velocity method provides crucial information about an exoplanet. From the period of the stellar wobble, we can determine the planet's orbital period. From the amplitude of the wobble, the maximum speed at which the star moves towards or away from us, we can infer the planet's minimum mass. It is a minimum mass because the method cannot determine the inclination of the planet's orbit relative to our line of sight. If we are viewing the orbit edge-on, the observed wobble represents the true mass. However, if the orbit is tilted, the true mass could be significantly larger, as we would only be seeing a component of the star's motion. This is known as the inclination degeneracy. Despite this limitation, the radial velocity method has been incredibly successful, leading to the discovery of hundreds of exoplanets. It is particularly effective at finding massive planets orbiting close to their stars, often referred to as hot Jupiters, because these create the largest and most easily detectable stellar wobbles. It also reveals planets in eccentric orbits, where their speed varies significantly, causing distinct patterns in the Doppler shifts. This method has helped us understand that planetary systems are far more diverse and varied than our own solar system initially led us to believe. Consider the profound implications of this invisible tug-of-war. We are not directly seeing these distant worlds, yet through the universal law of gravity and the subtle bending of light, we deduce their existence, their periods, even their approximate masses. This scientific detective work underscores the interconnectedness of the cosmos, where even the smallest gravitational interaction across vast stretches of space leaves an indelible mark, waiting for our sensitive instruments to decipher. It is a testament to the power of human ingenuity, allowing us to perceive the unseen, to expand our understanding of what constitutes a planetary system, and to contemplate the countless unseen worlds that shape the destinies of their parent stars. This gentle, rhythmic pulling, this cosmic dance, is but one of the elegant ways we peer into the grand tapestry of the universe, seeking out those distant lights that might harbor another Earth. The universe, in its intricate cosmic ballet, offers us another profound window into the presence of distant worlds, one that relies not on the subtle gravitational tugs we just explored, but on the delicate interplay of light and shadow. While the radial velocity method detects the star's dance, the transit method allows us to observe the planet's fleeting silhouette as it passes directly in front of its host star. This is perhaps one of the most intuitive ways to imagine detecting